Yeah, okay.
Good morning, everyone. So welcome to this third day GIAN course on operation and control of power converters for integration of renewable energy sources into the power grids. So yesterday and day before yesterday, last 2 day sessions were held on history regarding this power generation, microgrid, smart grid, how exactly the differs between both the architectures, and what exactly the architecture mean by microgrid and smart grid, and its further systems which are connected, the systems like renewables that are connected. So today we will be having session on the control and operation of grid connected AC-DC converters. So over to you, sir.
Thank you. Good morning, everybody. So it's pity that the other students have a delay or not coming because it's a little bit challenging topic today. So the title of chapter 4 is the control and operation of grid connected DC-AC converter. So at the end of this chapter, you will be able to classify different types of power converter, develop a dynamic model of a grid connected DC-AC converter, apply control strategy to operate grid connected converter under different operating conditions, and you will be able to design a control technique for injection of different actually power from energy sources to the power grid, and and you will be able to implement technique to compensate the harmonic and reactive power also in power grid, which are somehow connected by nonlinear loads. And also you can adjust the power factor of the grid by integration of energy sources, can be renewable energy or storage devices in main grid. So before we start, do we have any question, comment, concern, or something regarding the previous session? No. Okay, good. So the first topic is the classification of the power converters. Basically, I'm not going to say that this is something that famous as a classification of the power converters. When we are talking about the power converters, is 2-level, 3-level, 4-level, I don't know, H-bridge converter, diode clamp, or flying capacitor, this type of. But here we are going to talk about the grid following, grid forming, and grid supporting converters. So when we are talking about this type of topologies, basically converter can be conventional 2-level converters, depended where we are going to use. It can be also multi-level converters for high power applications. But the control technique we are using shape the operation of this type of converters. So the first category is grid following or grid feeding converters. So does anybody has any idea what is the grid feeding converter? I'm pretty sure that lots of, no? Okay. So this type of converters, yeah, tell me. Yeah, okay. Mm-hmm. You mean that, for example, grid connected? Mm-hmm. Yes. So, I mean, this is type of the conversion system that has actually is synchronized with the power grid based on the frequency and voltage, and they are providing electricity for the power grid. So if you have a source of energy, I don't know, 5 megawatt, then you're going to inject maximum active power to the grid. Then you should provide the grid following or grid feeding actually converter. So we have also grid forming converter. So this type of converter is, I mean, the conversion system is better to say, is working like a voltage source. So it has a small output impedance, which also provide the frequency and voltage, maintain the frequency and voltage, and can be used as a reference for the other converters. So you can consider this one like a grid, and then the other converter can be connected to this type of conversion system as a like a slave, and then follow the power injection. We have another type of actually conversion system. It's a grid supporting or grid connected. So in grid connected system is working like the same like a grid feeding or grid following system, but the difference is that this type of technology are mainly for the regulation of voltage and frequency in the grid. So in grid feeding, you provide the electricity and inject to the grid. So it means that you are going to provide the maximum active power to selling the grid. So if you are, for example, private sector that have a small power plant which can provide, I don't know, up to 10 megawatts, and you are going to sell it to distribution grid, you don't care that what is happening in the grid. You have some commitment to inject some power to the grid. So you should use the grid feeding. But when we are talking about the grid connected, it means that you have some problem in your system. So system is, I don't know, the voltage is not regulated, the current is not, I mean, the frequency is not regulated. Then you use this technology to provide active or reactive power based on the changes, and based on that you can regulate the voltage and frequency of the system to support the stability of the power grid. So, is it clear for everybody? Yeah. Grid support. I mean, this grid supporting can be grid following or grid forming, okay? But depended where you are going to use. So basically, they are two different applications, and this one is also support the stability of the grid, but it can act as a grid following or grid forming. Sorry? No, I'm saying that it has this possibility. So for example, if you have a microgrid, you cannot use the grid following because we have no grid to be connected. We need grid forming, okay? But if you have a grid supporting, it can work as a grid following, which we are in the grid connected mode, and it can also work in a grid forming when we are in isolated mode. So this is the difference. But when we are talking about the grid following, it works only, yeah. So now we get back to this one. We said that it is a DG, but it is not microgrid. Why? Because the converter we have here is working as a grid following. So when we don't have actually grid here, in fact, it cannot work, and then so it cannot shape the microgrid in the system. So now, if I ask what is the difference between these three configuration, 100% of you know, yeah? Where's the area? Okay, he's not. Abe, is it clear for you? If I ask you to come here and explain what is the difference, you can, yeah? Grid forming. Okay, this one. Okay. So now we know what is the difference between grid following and grid supporting. So now grid forming. Grid forming is a type of the converter or conversion system which can react as a voltage source. It means that it can create the own voltage and frequency. Okay? The difference from here and here is that they are following the voltage and frequency from the grid. But this is separate. So if you are going to, for example, create a power for 60 hertz, you can do it. 50 hertz, you can do it. 45, you can also do it. Okay? But for this case, you make the measurement from the grid and then tune the operation of the converter and react based on that. So if the grid current is or voltage is 50 hertz, it can create the 50 hertz because it measured the 50 hertz. So this is independent from the grid, but they are dependent. But in the case of the grid supporting, it can be also independent. So, clear enough? Mm-hmm. No, in grid supporting is the best application because it can work in isolated and grid connected mode. Grid forming cannot work in the grid connected mode because I mean, you can actually, but there are some synchronization, so you need the PLL. But the mission of this type of grid forming converter is we remove the PLL because PLL provides some actually is sensitive to the disturbances and yeah. Yes. Yeah. So this is also a good point that I'm going to repeat again. So in grid supporting, we use for the microgrid because grid supporting is able to work in both grid connected mode and isolated mode. Siddhant, did you get it? Do you remember what is the grid connected mode and isolated mode? No. So how is possible you get it without knowing that what is the... Okay, so let me explain again one time more about the grid connected mode and isolated mode. So this is our microgrid. So microgrid is a part of the grid which can disconnect it from the grid when we have some problem, and then we can return back to connection mode when problem is solved. So if you look at here, we have this static switch. So it means that we have actually some loads, some generation, so it can make the balance between the generation and consumption by energy management system. So then if some problem happen, we can be disconnected from so it means that we are in the isolated mode, okay? But when we connect to the grid, We are in the grid connected mode, okay? So now we get back to here, we see that we have three class of the conversion system. So grid following means that we follow the grid. So if grid frequency is 50, it's 50. And the idea is that we inject the power. So if you are committed to, or you have a small power plant, you are going to sell your electricity to distribution company, your responsibility is provide the electricity you promise it. But when we get back to grid forming is a type of the conversion system which create the voltage and frequency. So if you are over a mountain, so you are going to provide the electricity for a single load. You don't need to create the actually transmission line up to over the mountain. So you can use the grid forming conversion system and create the small grid with the frequency and voltage you need and support the load. For grid supporting, it can work both in grid connected mode and isolated mode. So if we have a microgrid, it can actually be disconnected from the grid and provide electricity. So this one acts as a grid forming like this, because it's like a source and load, that's all. But when it's connected to the grid, it can be grid connected mode because it should follow the frequency. Yeah. Yes. I mean, basically, it can be for the grid forming, you're saying, yeah? Yeah, for the grid forming, you can actually set some points that it provides some support to the grid. But the main idea is to provide the power to the grid. But if you set the point and set that, for example, if we use the drop controller and then we set the point between frequency between 90 to 51, then it can balance the voltage and frequency based on the active and reactive power injected to the grid, okay? But we will see how it works. So now it's important that you get the difference between these three categories, because lots of people make the mistake between the grid supporting and grid following, or grid connected and grid following converter. So this is the structure for the grid following or grid feeding power converters. So basically we have actually, the model is working like a current source with the parallel impedance, and this impedance is quite big. Does anybody knows that why it is big? Why? But transmission, you cannot, yesterday I discussed that, you cannot connect the converter to the transmission line. You should use the FAC devices. Yeah. The idea is that, for example, if you have a 1 ohm impedance, and then you parallel it with another 1 ohm, so the equivalent will be equal to 1 over 2, okay? But when you have 1 ohm and another is 100 ohm, is 1 times 200 plus 1 plus 100 is near to 1. So the impacts of this big impedance is not that much when you are working in the parallel connection, so it doesn't provide too much losses for the system. You can ignore it. So this type of actually system are working like an ideal current source, and we can also provide somehow power for the services, power for the grid by integration from the renewable energy source. Basically, we use the current control for this one, but the the requirement is that we need to have the voltage and frequency from the grid. Yesterday I said that for this case we use PLL to measure the frequency and an instantaneous angle of the grid, and based on that we can tune the controller and provide the electricity to the grid. And one important thing is that we use the PLL to know the instantaneous angle of the grid. So what is the meaning of instantaneous angle of the grid? And why do we need it? Does anybody has any comment about this? Why do we need it? So assuming you have this grid, three-phase system, you're supporting load, and you're going to connect your converter here. So this is three-phase, 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 okay? So we said that we need the PLL to measure the V1, V2, V3, and give it to PLL, and we have omega and theta. So V1, V2, V3. So what is the benefit of this such measurement? Why do we need it? Is important. So yeah. No. In the bottom they have something. So what is the benefit? Why do we need it?
We use it for the converter.
So what happens if we use it?
Thereby you are controlling the, I think the voltage.
Controlling the voltage. So, and
You
what
are
happened?
taking
Exactly. Yes. Thank you. Okay. So, then, okay. So, assuming this is the voltage, okay? So, voltage start from 0 to 1 period 2 pi, okay? This is the voltage of the grid. 1V start and then go to 2 pi, and again the same will be repeat. And I'm going to synchronize, connect this converter to this. So, and then inject the current. So assuming that this is the current of the grid which provided for the load. So before connection, the grid current is equal to load current. Okay? So now I'm going to connect this converter. But when I'm connecting, it's in this 37 degree. Okay? So if I connect without considering this phase shift, the current goes like this. Okay? So when we have here, here, the current of the grid is negative, I don't know, negative 10 or minus 10. Here is plus 3. In a state of we go to minus 13, we have minus 7. So in a state of supporting, we dampen. So it's not good. And the problem is that we didn't consider this instantaneous angle of the grid. So for this, we use the PLL to calculate the omega and theta, and when we tune our controller, we tune it based on the theta, instantaneous actually angle of the grid. So when we control the converter and when connect the converter to the grid, the converter inject the power based on the theta from the grid. So it should be something like this. So again, this is my grid, this is the voltage, this is the current of the grid for the load, and then if I connect it here, then it goes like this. Okay? So follow that one, the same angle. So the current can be something like this one. Okay? But it follows the same phase after transient time. So then if we reach here, the current of the converter is -3 and here is -10. Totally we can inject -13 ampere. And here also if it is 4 and it is 7, we can inject 4 plus 7. Okay, so we support it. So this I1 will be added to I2 and create I3. What is the benefit? So if the I3 increase more, which increase the stress over the grid, then this I1 converter current can support this current and reduce the stress over the grid. Is it clear? So for this, we use the PLL to measure the instantaneous angle of the grid, and based on that, we provide the synchronization between the grid and converter. So this is something that we need. But in grid forming converter, it acts as actually voltage source with the small z. So here is big one. But in second, we have a small. Why? Because if we increase the impedance, in fact, we have more losses in series connection. So in this type of control, it works as a voltage source, and it can provide the voltage and frequency based on what we need. So if you are, for example, somewhere remote that you have no access to the grid, you can, for example, you need a load. You buy this load from the USA, and then in USA the frequency is 60 with 110 volt, but in India is 220 with 50 hertz. So what should we do? Nothing. We don't need to buy from the grid. We should create it. We use the grid forming converter, but grid forming converter can be tuned in a way that creates the 110 volt with 60 hertz. So it has this benefit. So, but in the big power plants, okay, so assuming that you have a power plant, you are going to create the power for a grid. So grid means that transmission and distribution grid. There is no generator, nothing. So you will be power plant, assuming that you had actually nuclear power plant. Now you are going to replace by renewable energy. It can be wind or solar or something else. So what can we do is that we create a grid forming, and then the rest of the converter can be follow the grid forming as a grid following. So by this assumption, we can create a grid, and after that, this power plant can be considered like a voltage source, and then transfer it to the transmission line, distribution, and then consumption. Is it clear enough? So this frequency can be created by the grid forming converter of frequency and voltage. So mainly for the power plant, frequency is important, because then we have the transformer. We can actually change the level of the voltage. So is it clear, or Why you're not saying anything? Clear? Okay, thank you. So then you have another topology, grid supporting, that we discussed. So we said that it can be like a actually current source or voltage source. All of this getting back to the control loop we are considering. So it can act mainly in microgrid. When we have actually in isolated mode, we can support actually electricity for the load that we are previously used the grid. But when we are in grid connected mode, the mode of this system can also change and can provide the electricity based on the situation of the grid. So, but the main idea is that we regulate the voltage and frequency of the grid. So if something happening, for assuming that you have a network, short circuit happening, and we have a huge amount of the current go to somewhere which this short circuit happened, then what we can do is that we use such a technology that increase the, because when we have a high current, short circuit current, then the voltage drop. It means that we have some problem with the voltage. So this converter can increase the actually reactive power to provide or regulate the voltage. And there are some other things that, for example, we have a huge amount of the active load that change the frequency of the system. So by this, we can provide the actually, we later see this group controller to provide the regulation for the voltage and frequency of the system. So this is very useful technology that can support the stability of the grid. But when you have actually your provider for the distribution company, you have some commitment to meet it, because distribution companies sell the electricity based on what you promise to them. So by this assumption, if you are going to compensate, the best is using the this model. Okay, you see that we have the grid, and when the grid is stressed or is faulted, then we can provide the electricity actually from the generation for the local load. Okay, is it clear up to here? So, but assuming that you are going to, for example, supply by these storage devices, you have a DC AC converter. This converter should work as a grid supporting, okay, because it should be able to create the voltage and frequency we need. But the difference from this one, from the and grid forming converter, is that this converter is following the reference based on the grid. So if grid is disconnected but the frequency was 50, it has information that the frequency is 50. Okay? But in grid forming, you can form it. You can say that the frequency is 70, 60, I don't know, 40. You can decide based on the demand. Okay? So by this, when we return back to the grid connected mode, again it works like a current source and provide actually power to this bus, and if we have extra power, we can also consider for the grid. Yeah. But the difference is that in grid forming, we don't need to have the PLL. But in grid supporting, we need to have PLL. Yeah, this is the difference between these two technology when they are working in isolated mode. You mean from the grid connected to islanding mode? So we have this static transfer switching, static STS, static transfer switching. So it detects the voltage and frequency of the system, I mean the network, and if we pass this limitation, the border of the limitation, it means that we have the problem in the grid. So for example, if short circuit happening, we have the voltage drop, and you can see that there are some problems. So it is better that we get, otherwise our system will be, our load will be damaged. Okay, so basically based on the monitoring, but there are some other techniques. So for example, you can get the information from the distribution company about the price of the grid electricity. So it depends if you are going to maximize the benefit from customer point of view. In fact, you can be disconnected from the grid and operate in islanding mode because you can provide electricity by yourself for the your load. So there are two different points: grid point of view or customer point of view. Is it clear? Good. Any questions so far? You're taking this one? Yeah. Okay. Mm-hmm. Mm-hmm. Yes. Yeah, some here you mean? I mean, basically this is based on the group controller, okay? So they said that delta frequency is equal to C or K or something times to delta P, or delta P is equal to Cp times to delta omega. So it means that when we have the changes, delta F, so delta F is the frequency changes. So you have the reference in 50 hertz. So your reference frequency is constant, okay? But what you consider as a grid frequency is something different. So assuming that your grid has some event and the frequency change between 49 to 51. So you can define delta V between 49 up to 51 is fine. But when it goes to less, like a 48, then it works. So delta P should change because P is a constant value. And then they said, for example, now I inject 10 kilowatt, but the frequency drop. When the frequency drop, it means that we need increase the active power to return back frequency to this borderline. So by this, you increase the actually value of the active power, then compensate the frequency of the system. And for the reactive power is also the same. So later we see, I didn't go through the mathematical equation, but later we see that equation that, when we have delta Q, or a reactive power change, is equal to a constant value times to delta V, because we can control the voltage based on the reactive power. So, for example, we usually said that the voltage runs between 5% is okay. But when you pass the 5%, so it means that you have some problem in the reactive power of the system. So you should increase the value of the reactive power injected from the source to the grid. So basically, it can be somehow, because the power injected from the converter to the grid is a constant value. But in the fault time, when we have the problem in voltage and frequency, you can play with the active power and reactive power. So, for example, 10 is equal to so in converter S is equal to P plus JQ. Okay? So, for example, 10 is equal to 6 plus J8. 10 is equal to 8 plus J6. Okay? So, it means that the active power can be 6 or 8. If the frequency is dropping, we can increase the value of the active power. And if the voltage is dropping, we can actually increase the value of the reactive power. So this is the difference between grid connected mode and grid following mode. In grid following mode, they don't care. They said that this is my commitment, I should inject 10 kilowatt. What is happening in the grid is not my business. I have some commitment to provide that much electricity for the grid. But in the grid supporting or grid connected, the main idea is that to regulate the voltage and frequency by injecting. You can inject active and reactive power basically when we have no problem, because the main idea for integration of renewable energy is the injection of the active power to the grid. But only active power is not enough for the stability, so we should provide the reactive power. But the share of the reactive power is much more, less than active power. So just a simple example in this OACOPC project, they have a unit with 1 megawatt active power, but they had also 50 kilowatt reactive power. So the idea was the injection maximum active power, but the reactive power is also needed for the stability of the system. But the difference is active power is 10 times to 20 times more than the reactive power. Okay? You got the point? Okay, good. Any question? Yes. Yes. This is also the same assumption because it's possible to play. But what we are discussing in circuit theory is the equivalent with the Thevenin model and Norton model. What I can say, it's dependent to the control operation. So in this operating condition, we jump from the current control mode to the voltage control mode. And the difference between this technology and grid following converter is that in grid following converter, we just follow we control just the control of the current. But here we have the combination of we have a two-stage. We have inner and outer control loop. So in first stage, we provide the current control loop, but when we jump from the connected mode to isolated mode, it jumps from the current to voltage control mode. So this is we have the two stage of the control, but in that we have just one stage of the control. Yeah. Yeah, as long as we are researcher, I can say yes, we can, but you should decide to go forward for that or not. Which component? That one. Basically, when we are talking about, but you should tell me clear that in which mode. If you are talking about for example, power plant, or you are talking about the small.
How we can decide this is
Yeah, I'm saying that if we are in isolated mode, we go to the voltage control mode because we have no voltage reference. But when we are in a grid connected mode, because we need to be synchronized, we get the information from the grid and it goes to the current control mode. And later you see that why we should do it. Do you have any other question? Okay. Because do you know what is this QP? I mean, the Park transformation and how we can control the converter? Mm-hmm. Mm-hmm. Yes, but we need the theta, okay? Because we have this Park transformation which is based on the theta, and this theta is coming from the grid. So when you get the grid theta, it means that you control the converter based on the theta from the grid. So anything happen in the grid, you can see in the control loop of the converter. Then the converter can react based on the situation of the grid. This is the reason. Yeah. So, any questions so far? Is it clear for you? Okay, when you don't say anything, I really don't know it's clear or it's not clear. It's clear, good. I mean, it's a basic. If you say that it is not clear, so what should we do then later? Okay, Arya is not here, yeah? Tell him that it was biggest lose of his life. Okay. So, now we get back again the characteristic of grid following converter. If you see that we normally use the PLL for that one when we are in grid connected mode. So basically we can regulate the active and reactive power of the system based on the control of the active and reactive current. And just we cannot say that active current or reactive current. But later we can see that, you know, there is because the voltage is constant or must be constant, then the active power is somehow related to the current, and reactive power is also related to the current. So this is why we said that, you know, they are somehow controllable based on the control of the active and reactive current. So in fact we can control the P and Q based on the current. So we also have the current set point. It's somehow calculated based on the needed value that we need for the regulation of the or the injection of the power. So we cannot say that, you know, this is our system. We can actually inject whatever you want. You need this to provide the set point, and based on that you can inject. So the simple example is the OACOPC project. I mentioned that we have 1 megawatt active power, 50 kilowatt reactive. So it means that the converter is responsible to inject that much active, that much, because the set point is for that one. And mainly this happening when we are actually in power plants. It is very important to consider that one. So, any questions so far? So if you consider the structure, always it's follow based on the actually PLL, the theta getting from the PLL. And there is some problem because when we go through the PLL, then if fault happening, then the control loop get in the problematic situation. So we need to consider also some extra feature in the control loop of the converter. For example, if the fault happening, the fault right-through capability is something we should consider. in the control loop of the converter. So for this reason, only considering the current control loop for that types of the converter is not enough for the power grid. You have one option to just inject to the distribution power station, and after that, or if you are going to connect to the load center, then you should consider some extra feature is also needed. Look, any questions so far? No? Okay. So this is also the other part. I mean, we somehow consider the active and reactive power injection by controlling the voltage and phasor amplitude. So at the point of common coupling, and the reason for this grid forming technology, which we consider based on the PLL, is that based on the grid is, does anybody knows? We said that, you know, we don't need PLL, but in reality, we should consider the voltage and frequency of the grid for the grid forming converter. So does anybody know why? We can say that we provide power based on the voltage and frequency we need. But now we can say that based on the point of common coupling. So common coupling means the grid, the point that converter is connected to the grid. Does anybody knows that there is some contradiction? Yeah? Does anybody knows why? What? I mean, one thing is the grid code. Yeah, you cannot be connected to the grid. Does anybody knows what is the grid code? Okay. No, grid code. Grid code is some actually rules that the country define. So they said that you can, for example, provide electricity, but for the connection to the grid, you need follow some rules. So this is why the Chinese said that you can provide electricity for yourself, but you cannot inject to the grid. Why? Because it makes some problems. So grid code said that if you are going to, I mean, basically any component with, it can be trans, it can be converter, it can be anything that you, but you need to actually follow the grid code. So, just a simple example. Grid code said that you can provide electricity and integrate to the grid if the THD is less than 5%. So it means that your power should have the high quality. And if it is 6%, it means that it is not in the standard that we are actually we need. So for this case, you can actually generate it, you can use it, but you cannot inject to our grid because our grid standard is less than 5%. Okay, so this is the something that you need to follow. And the other thing is that you are going to create a power plant, and we said that we use the grid forming converter. Then the grid forming converter should follow the grid. It means that the grid has the situation at the end you are going to connect this power plant to the grid. So it is good to follow the grid in the right one. This is why that when we have actually like a multiple system, it is better that we have a synchronization with the grid. There are some other actually technology that you can be synchronized with the grid without using the PLL, but the best is that we have reference from that. Any question? Okay, good. Harmonic? THD 5%. Yes. No, current is different story. And we are not talking, because current is returning back to the customer side, and customer is normally non-linear. It can be, I don't know, 20, 25, anything, okay? Yeah, but in the ideal situation, customers are not also connecting non-linear load to the grid. Okay, this is why actually distribution company give the penalty to them. Okay, but in power quality, yesterday I talked, when we are talking about the power quality, in fact, we are talking about the voltage quality. So at the end of the day, if you are going to provide electricity to the grid, it should be both the THD of the current and voltage should be less than 5% THD. But in the load side, we are responsible as a DSO to provide the voltage less than 5%, but the current is dependent to the customer side. Okay? Udaya, did you sleep well last night? Yeah, I feel a little bit sleepy. Yeah, okay, good. So, sit down. What happened after dinner? You went to party or you? Okay, yeah, seems that you are sleepy now and the other guys are not. Okay, now I got the point. Okay. So you're touristic visitor student. Okay, good. It's one shot for 3 targets. Okay, good. So, any questions so far? No. So now we are going to talk about we talk about the 3 class of the conversion. And if I'm going to tease your coordinator, Mr. Udaya, then he's going to one time forever actually repeat that what kind of technology do we have. So I'm talking about these 3 things. So tell us, Udaya. Grid forming, grid following, grid connecting. Yeah. What kind of classification we have for the conversion system? Mm-hmm. Mm-hmm. Yes. Yeah. Yes. Yeah, we have 3. This is something that I emphasized at the beginning, and Udaya answered my question 100% correct. I said that what kind of conversion system do we have? He said that DC-AC, DC-DC, AC-DC, and AC-AC is 100% correct. And then just the idea for asking this question from Udaya is that because he was absent, and I'm going to make sure that you understand this type of technique is the conversion system, is not the class of converter, okay? But they normally said that classification of power converters. So, based on this topic, they said that Udaya's answer is 100% correct, and thank you for precise answer. But when we say that, grid forming converter is not the converter, it's a conversion system, okay? So converter can be normally just conventional 2-level converter, but it is controlled in a way to react as a voltage source. So later, if someone asks you, what is the grid forming converter? You said that this is the type of the conversion system which acts as a voltage source. And what is the grid following converter? This is the types of the conversion system act as a current source. What is the grid connected? It is the type of conversion system can act as a voltage or current source in the network. So now it was the introduction of this conversion system. Now we are going to talk about the Park and Clark transformation. So how many of you guys know that what is the Park and what is the Clark transformation system? Just raise your hand. 1, 2, 3, 4. Okay, good. I'm pretty sure that you know it. You know it. You are trying to say that I don't know it. Yes, they know also, but they are tired. Yeah, okay, so, yeah. So, Udaya, you don't know, yeah? Okay. So, okay. Anyway, so we have actually Park transformation is a type of actually transforming from 3 dimension to 2 dimension. So we have A, B, C. Okay, by this matrix, we transfer it from A, B, C to DQ. Okay, just look at this one. When the angle change, look at this angle. When the angle change, because the voltage is changing from the 0 to 360. Okay, when the angle change, the position of D and Q change. So, but this position is not somehow, the value of the VD and VQ is not the constant. So it goes up, down, and they follow based on this equation. So if you have a function in ABC, so you can times to this one and provide the DQ. But if the system is unbalanced, we have another actually point, we call it 0. So it can be another 3 dimension matrix consists of D, Q, 0. But in this course, we are going to talk about the DQ. So we have a constant value 1 over 2, 1 over 2, 1 over 2. So assuming that you have VA, VB, VC. So VA, VB, VC. So if you times this one to VA, VB, VC, so at the end of the line, you see that 1 over 2 times 2 V0 is equal 1 over 2 VA, 1 over 2 VB, 1 over 2 VC. 1 over 2 VA plus VB plus VC. What is the value of this? In balanced system, VA plus VB plus VC is equal to 0. So it is equal to 0. This is why we convert it VD, VQ, and this V0 is equal to 0 in balanced system. Any questions so far? Now the question is that, okay, we are going to change it from A, B, C to DQ. What is happening? Why we should actually eat the food by this way? Is there any benefit for us? Is there any food? Yes, it is. Okay. Does anybody have any? Yeah. Why control will be easy? We change from 3 variables to 2 variables. Okay. Good question. Good answer. But it's not complete. Siddhant, do you have any idea? Okay. Sorry? Exactly. This is what I'm looking for. Thank you. So when we change from ABC to DQ, so first that we change from 3 dimension to 2 dimension, and second, if you look at here, we change from sinusoidal to the DC value. And then, so let's go to the next part. If our input is this one, A, B, C, the output will be constant value. So assuming that you have actually a system with the harmonic, and you change it from ABC to DQ, so the fundamental frequency become DC value, and the harmonic frequency will be something else. So by use of the filter, you can actually separate the fundamental frequency easier by harmonic, and then you can make the compensation in the control. So for example, just a simple example. So assuming that this is my converter, DC AC converter, and this is my source, and this is filter, and this is load. So I'm going to compensate or provide the electricity from this source to this load. So this is I load. So I said that, okay, I get IL1, IL2, IL3, and convert it to ILD, ILQ by Park transformation. Okay, up to here is just a transformation. Then I said that my load is somehow nonlinear. So then it can be split to two parts. If I draw this one, ILD can be fundamental frequency and harmonic. I said that when we change from ABC to the O, the Q, the fundamental frequency in DQ will be DC value. So this is my DC value, but the harmonic is harmonic. Then I use a low pass filter, then give this ILD and just get the fundamental frequency as output. Okay? And I just make this one fundamental frequency, and this is ILD. ILD plus minus. So what will be output? Harmonic. Okay? So now I use this one as a reference for my converter. I say that, okay, this is I harmonic, and then please compensate the harmonic. Okay? So the rest of the load will be supported by the grid. So harmonic will be from here, fundamental frequency will be here. Yeah? So IL is equal to I fundamental frequency plus I harmonic. I harmonic is coming from converter. So fundamental frequency is coming from here. You see, the control will be extremely easy for us when we transfer from ABC to ODQ. And then another benefit is that you can actually split the currents to different, I don't know, harmonic, reactive power, fundamental frequency, and you can inject the maximum available power. So based on that, you can prioritize that, you know, if your system is going to compensate the reactive power or harmonic or active power. So different applications, we can play with the reference and provide different services. So now I'm going to simply ask a question. Assuming that you have a company, that the company has a lots of nonlinear load. So do you believe that you can support these loads from the grid? You. What is your name? Ash? Rakesh. Okay, Rakesh. It's quite easy. Rakesh? So, next targeted student. Rakesh, do you have any idea that we can connect this nonlinear load without any problem to the grid? Yes or no? Yes. Very simple political answer. Yes. Yeah, definitely we can actually, because we need to supply the load, Rakesh. Okay. So then we get back a little bit this side, in the grid side. So assuming that you have a power plant and this is in the Atacama Desert, and I said that the idea is that we provide the electricity from solar, and each unit can provide 1 megawatt active power and 50 kilovolt ampere reactive. Yeah, reactive power is actually for the stability of the system. This active power is in fundamental frequency, if I'm not wrong. Yeah, you provide electricity with the 50 hertz and the voltage PhD less than 5%. So how is possible? Your system is nonlinear. You need the nonlinears, but your generation is linear with the 50 hertz. What is happening between? What?
Reactive power compensation like that.
Compensation.
At the low end, we have to provide reactive power compensation. Like
But I'm talking about harmonic, not reactive power. Okay? But now my question is that it's a little bit confusing, yeah? We have a nonlinear. Rakesh said that we can connect it, but I said that I don't have actually harmonic, so what is happening? So it means that you make some disturbance for the grid. Am I right? So then what is happening? Then the distribution company said that, no, you are not allowed to be connected. You should compensate your system, your load. Otherwise, you should pay 10 times penalty, because you make the grid unstable and then it affects the other loads also. So you cannot. So what should we do? Now, for example, we have actually very smart expert engineer. What was your name? Ross. Ross is also easy. Rakesh Ross. Okay. So, Ross, what is your solution for this one? Okay, you're not listening me. Now, I'm saying that, do you have any solution to solve this problem or not? You prefer, as the owner of this load, pay 10 times penalty, or you use a smart. If my father was like this one, he fight with the distribution company and said that if I pay 100 times more, I will not actually change my system. So it is not a smart solution. Okay? But do you have a smart, cheap, smooth solution for that one? Compensation. This is also, they are very actually good to be lawyer, something. Yeah, compensation, yeah. Mm-hmm. Yes, I agree. So, but now I'm talking about the harmonic. But yeah, you're right actually. Power factor is also one important factor that after that we will discuss about that. Yeah, like filters. What kind of filter? Passive filter, active filter, low pass filter, high pass filter. Which? What? Active, excellent. Active power filter. Active power filter means that we provide the harmonic part of the load, and then the linear part can be compensated by the grid. So I can say that, okay, so I'm owner of the company. I don't like to pay penalty. And Ross is a very excellent, super intelligent expert in this concept. I get the idea that how we can solve the problem. And he said that, okay, so I'm expensive, so you should pay 5,000 euro. I will check it for you and fix it for you. So I use actually a local power generation. So in the corner of my company, I set the PV or storage devices, and then compensate the harmonic by this system, and then the grid can be free of harmonic. So we can provide harmonic from the local power generation. So the reason for this question is that you can change the controller based on your actually demand. So in this case, you are going to use this one for the harmonic current compensation, as Rose said, the compensation. But as Somi also said that, reactive power. In some cases, you have the reactive load, which change the power factor of the grid, and distribution company again ask you to compensate it. Otherwise, you should pay the penalty. So for this case, in the conventional technology, they use this capacitor bank to compensate the reactive actually power in the load side. But the smart solution nowadays is that we use this technique. It means that we just provide the reference from IL and then split it to ILD and ILQ, and later we can see the ILQ will be reactive power and ILD will be active power. But it is not always like this. It depended how you calculate it. You will see it. And then I asked the converter to provide the reactive power based on this reference. And based on this, we inject just ILQ, and ILD is coming here. It means that reactive power is coming from the converter, active power is coming from the grid. So it means that this is power factor is equal to P2 plus Q2. So when Q is 0 in grid side, so power factor will be equal to 1. Okay? So all in all, you can tune your converter, and based on the demand, you can control it and get the maximum benefit. And there are another option. So the first option was the active power filtering. So we call it active power filter. It means that we compensate the harmonic. This one is the power factor correction. So if you have extra power, you can merge all of them. You said that I'm going to compensate the harmonic, active power, and if we have extra power, then we can also provide some part of active power in the fundamental frequency. We see later. Udaya, you want to have some break? Seems that you are tired. Yeah, okay. Good. Okay. So, can we start? Udeya? Okay, good. So, now we know that the park transformation and what is the main objective we using the park transformation. There are some drawbacks also we can see later, but as we are engineer, we should be happy as long as we have the problem in the system. It means that we can earn more money. Okay, so you should be happy. And one mission of the engineer is that when you finish the first problem, it is the starting point for the next problem. Okay, so your life is like this. Yeah. So we learn by this one. Okay, so if you reach in the point that you feel that you solved all the problem of the board, it means that you should not be too much happy for that one. I sent the paper to IEEE Transaction Industrial Electronic, and 5 of them answer positive, but with some comments. Then 3 of them accepted after first revision. Then I noticed that one of them gave a different comment again, new comment. And then I answered that one, and number 4 accepted, but number 5 give another new comment. And then I answered to this one, and he provide, because after 2 rounds, they should make the decision, but they provide again new comment. I said, okay, so this project, this paper will be rejected. So let me write something harsh to them, then they reject, and at least I feel a little bit more happy. So I said that, sir, do you believe that the controller you're developing should solve all the problem of the world? And then editor-in-chief actually make the decision, as you mentioned, this is correct, your controller cannot cannot solve all the problem of the world, so your paper is accepted now. So yeah, it was very logical actually. Anyway, so if you reach that point, you shouldn't be happy. It means that you cannot learn new things. And one thing I can promise you, as an engineer, if you learn how to control the converter, always you have a good opportunity to get a good job. It's not something that, after 5 years you have no, because this is a roadmap for the countries, for all countries, that to reach the carbon neutrality by 2050. I don't know, do we have some roadmap in India yet or not? Yeah, 2070. Yeah, it makes sense because, it's a big country, and then, when we reach, we think about the 2070, it doesn't mean that, we're reaching the point, probably in 2035, we reach that, renewable energy probably create more problem for us. It's possible. We start to integrate the renewable energy before, I don't know, in the beginning of 2000. Then when we reach 2009, 10, we noticed that when we increase the level of the renewable energy, we have the instability in the frequency of the system. And then they noticed that this is due to the lack of the inertia. So when we reach 2020, they defined the grid code that you are not allowed to integrate your converter to the grid if you cannot provide the inertia for that one. And in 2022, 3, something like, they have some project that they claim that if we provide 1.5% based on the 10% increment in the renewable energy, the share of kinetic energy should be 1.5% to keep the stability of the system. And then nowadays, again, we get the problem that, this type of technology is not, we cannot actually store it, and the temperature and the radiation, the speed of the wind, they are not a constant, so it provides the dynamic issue for the grid, so it is better that we use the hydrogen technology. And then now we said that, okay, hydrogen is not that much fast. So we need to provide another technology to provide also fast stability compensation for our system. And the other is that, we have a very less efficiency. So for example, when we use the wind to electricity, the efficiency is 85%, something like this. But for the hydrogen, it's between 10 to 22%. It's very low. So this is the problem. But the good news is that as long as we have such problem, we need the people to work to solve this problem. So the job market will be also good for us. So I can say that it is better that you learn this one with me or without me, then later you have actually good chance to get a good job. Okay? Siddhant? So you feel sleepy today. Yeah, I noticed that. Okay. And Rakesh, okay. And Rose. Oh, my friends are growing actually. It's the equivalent of the integration of actually increasement of your penetration of renewable energy and penetration of Indian friends in my my list. Okay, good. It's always pleasure to have Indian friends. Okay, good. Now we talk about this park transformation. It is somehow very useful. There are some drawbacks, but there is also some good solution for that one. We will see later. But there is another useful tool. I mean, we don't consider this one as a controller, as a, I don't know, nothing. This is a tool. That's all. You can use it or you can use something else. Okay? So, we have another so we have another transformation. Actually, we say it Clark transformation. It's also the same, but the matrix we are using is not like a previous one. So we have actually theta here. So theta is changing, but in any time we have actually a constant value. So we have something constant, we create it. But for the next one, we have just a constant times to the sinusoidal value is a sinusoidal value. So the dimension is changing, but we also have this possibility to convert from 3-dimension to 2-dimension. Again, if you have an unbalanced system, we have alpha, beta, 0. Okay? So this is the reverse one. So we see that, the 3-phase can be changed to the 2-phase, but with the sinusoidal and different amplitude. So in each time when the theta is changing, the value is changing also. So the benefit of this is like a complementary side of the DQ, but there are some benefit in alpha beta in comparison with the DQ, but DQ is more flexible because we can separate the fundamental frequency with the variable frequency, and then compensation is much more easier for us. But up to here, there is nothing behind of this technology. We see that, okay, this is a matrix. We change it from 3-phase to 2-phase, and then we use later for the controller. And if you don't know where we can use it, you don't know it, this is not you shouldn't be worried, because this is part of our class. So now we get back to what we discussed as a beginning. We always said that we have a grid, we have an impedance of the grid, we have nonlinear load connected to grid, we have the converter, so then we have a filter and cable and transformer. So we have the model of the system, show it like equivalent of the impedance of the whole connection between the converter to the grid. We can also provide the DG source as a current source. So now we see that this is the general model, and now we are going to see how we can control this converter. So before we start, does anybody have any question? Is it this general structure, is it clear for you? So assuming we have a grid supplying the load, and we have a converter which we have a source here, and we are going to inject power to the grid and support the grid to supply the load and provide a stable operating condition for that one. So based on what we discussed, this is a grid connected converter. So it follows the voltage and frequency of the system, and then it can actually support the stability of the grid. If something happening here in the voltage or the frequency, we can play with the voltage and frequency of the with the active and reactive of the injected power and keep the stability of the system. Okay. Then now we are going to initiate a controller for that one. So, Costa, what is the idea and what is the intention to provide this control technique? So, okay. I mean, the idea is that, you remember yesterday I said that converter is like a vehicle. You have a Mercedes-Benz, but you should know how to drive. So controller is like your expertise to drive it and control it. You can go fast, you can go slow, you can go, I don't know, opposite side, the right side, you pass the other. So you should know how inject the power and what kind of actually power is needed. To draw a control technique for the operation of the converter, we need to have the dynamic model of the system. So in a converter, the voltage of the leg is equal to voltage of the phase plus the voltage of the neutral point. So I try to explain the control technique or design of the control technique as easy as possible. I can promise you, if you listen to it, you will learn it from the scratch. But I can also promise if you miss one part, you will not learn it. So if you don't learn it, it means that you didn't listen to me, okay? So basically, this is our converter. So converter can be connected like this one or like this one. This is the converter. Sorry. So it can be connected like this. This is my source. Source can be anything, wind, solar, battery, anything. But DC, AC, So, and it can be great. So R L. So this is I. Okay. So in converter we have conventional converter. We have 6 transistors. So in each leg we have 2 transistors. So VA is S2 VDC. So VA. So what is the meaning of this? So for example, this leg, they are complementary. It can be on, this is off. Or when this is off, on, this is off. So what happens if we send a switching actually signal to turn both of them on? Short circuit will happen. Okay? So assuming that this is on, so this should be off. Okay? Do you agree? So what is happening? So if this is on, it means that it conduct like this, and when this is off means that this is on like a. Okay? So it should be VDC. VDC, this voltage is this voltage. So VA will be VDC. And the other part, when this is off and this is on, it makes this one on and open, and this will be conducting, and VA will be equal to 0. Okay? So we can conclude that in converter VA is S2 VDC, VB also is S1 S2 VDC, VC is S3 VDC. You see here? So in fact, we mentioned that leg voltage, this voltage V1M, which is S1 VDC, is equal to voltage of the phase V1 from here to here, we call it 1, 1 or whatever you want, okay, plus VNM. So it can be N, and this is the neutral point for here, M. Okay? Voltage of the phase plus voltage of the neutral point. Is it clear for everybody? It's from the power electronic. I can actually somehow prove it, but it takes 1 hour. If you want, I can do it, or you can accept it. This is the basic of the power electronics. So now we see that V1M is V1K plus VNM. V2M is V2K plus VNM. V3M is V3K plus VNM. Is it 100% clear? Okay. So now we actually make this summation of this V1M, V2M, V3M is equal to V1K, V2K, V3K plus 3 VNM. Yeah? So we have a balance system. It means that V1M, V2M plus V3M is equal to V1 and this one. This one will be equal to 0. But this one is not 0. V1M, V2M, V3M is not 0. Why? We have the balance system. The output of the converter should be balanced. Any idea? No. So, do you know why? Remember that coffee? I asked them that, do you know why Indian put the sugar in the coffee and do this, but Italian put the sugar, do this, and Finnish put the sugar and do this? And nobody could answer. Do you know why? I mean, yeah, they are going to solve the sugar in the coffee. Yeah, this is just the intention. And the idea for this question is that we don't make simple issue big for us. The answer is they are going to actually make it sweet and drink. This is the idea, the answer. So, now I ask that why? Why this is not equal to 0, but this is equal to 0? So we see that the balance system is okay here. So in fact, we have a 120-degree phase shift, so it's equal to 0. But this is not equal to 0. Why? Because if you look at here, V1M is S1 VDC, V2M is S2 VDC, V3M is S2 3 VDC. So S1, S2, S3 are different. And if you look at the switching pattern, if we just neglect the 0, 0, 0 and 1, 1, 1, it is 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 2, 3, 4, 5, 6. All right? This is the switching. So none of them are the same. Yeah. We have actually 0, 0, 0, 1, 1, 1. Yeah. So 1, 1, 1 and 0, 0, 0, they are equal to. So then, if we consider this switching pattern, you see that we have nothing that, show that, in one operating condition, the output are the same. So, Costa, what is the meaning of 1, 1, 0? But what is the meaning? Are you Costa? Okay. Yes. Yeah. Yes, but they are complementary of each other. Okay? So when this happens, so Costa, tell me what is happening. What is the meaning of 1, 0, 0? Exactly. So when we say that 1, 0, 1, it means that this S1 is on, S2 is off, S3 is off, S5 is off, S2 is off, S4 is on because they are complementary, and S6 is on. Okay? So how is possible that by this operating condition we said that V1M, V2M, V3M is equal to 0? So it is impossible because the switching pattern are different. So we cannot say, so this is equal to 0, so VNM will be equal to V1M, voltage of the phase 1, leg 1, voltage of phase 2, voltage of leg 3 over to 3. Okay? Very easy. You see, the control of the converter started extremely easy way. So, now we go to the next part. if we are going to actually draw a appropriate control technique, we need to consider the dynamic model of the system. Sir, what is your name? Your. Yes. J. 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 J or Ajay? J. Okay, J. Okay. So, I know your name now. J. So, do you know why we need to have the dynamic model of the system? To make the suitable control technique, to design the suitable control technique? No. Does anybody knows? Okay. So assuming that you're going to go to the tailor shop and ask to make the actually pants for you. So he should know what is the size and everything, okay? So this is like this one. So if you don't know what is the system, what is the dynamic of the system, what kind of grid you are going to be interacting, what is the angle of the grid, what is the frequency of the grid, what is the actually voltage drop between grid and converter, what kind of sources do you have? If you don't have these type of things, you cannot control it in a right way. Okay? So for this, we need to have a system which reflects all the information from grid to us and from the converter and from the generation. So we call it from the generation interface and the load. Grid can be load because can be considered as a load, but it can be also just a load. Because when we integrate with the current, with the grid, we should inject the current to that one. In fact, we supply something, so grid can be considered as a load, but doesn't matter. So now we see this stupid question, equation, and especially for the bachelor level, it seems a little bit complicated, okay? But I know that you are brilliant, intelligent student, and you can actually make everything easy for yourself. So I can explain from this and said that, okay, this is the method, and then you go that equations, but Udaya asked me to go from finish way. So I'm going to make a little bit more easy for you. So then you will see that the design of the controller for the converter is not that much complicated as it seems. So, what is that? We have a converter, yes? So we have V1M here. Yeah? Then we have R, L, and V1. Do you agree? This is what we have here. It seems like a Godzilla, but this is this. Okay? And we said that the voltage, Udaya, what is the KVL? Doesn't matter, current is coming from converter to there, they mentioned from grid to converter, but assuming from this one, I. Tell me, Udaya, minus V1M place RI plus LDI dt plus V1 plus neutral point VNM is equal to 0. Do you agree by this? Okay? So let's get back to that one to see that I made a big mistake or not. So, basically the direction is different. So here is from here to here, but the direction of the current, but I got from there. So let's get back to the model we have here. And because we are going to compare to make sure that this is correct or not. I. So minus V1 plus LDI to dt plus Ri plus V1m plus Vmn is equal to 0. I hope it is correct. Minus V1 plus LDI to dt plus Ri plus V1m and Vmn is equal to 0. Thank God it is correct. Okay, so you see, it's nothing complicated. Yeah? And if get back to three-phase, so we see that minus V2 plus LDI2 to dt plus Ri2 plus V2m plus Vmn is equal to 0. Minus V3 plus LDI3 plus Ri3 plus V3m plus Vmn is equal to 0. Yeah, like this. So simply transfer this to other side and write this one like this. Okay? Is there anything that is not clear for you? It's clear. Yeah, even sit down, say clear. Yeah, okay. So, now we have three-phase balance system. V1 plus V2 plus V3 is equal to 0. L di d2 dt I1 plus I2 plus I3 is equal to 0. R times 2 I1 plus I2 plus I3 is equal to 0. Plus V1m, V2m, V3m plus 3 Vmn. And again, we see that V1m plus V2m plus V3m equal to 3 Vmn. So Vmn is equal to minus V1m plus V2m plus V3m over 3 is equal to minus 1 over 1, 3 sigma Vmn, m from 1 to 3. Nothing is completely, if Costa is not feeling sleepy, easily can understand it. Yeah? Good. So, now get back to the equation again. Because he mentioned here this is the model of this grid connected system. And now we are going to talk about the dynamic model of the system. And let me ask a question from you. What was your name? Tutika? Grutika, I remember. Grutika, tell me. Your name is a little bit hard. Grutika. Okay, Grutika, what is the meaning of dynamic? We have a dynamic atmosphere, we have a dynamic weather, we have a dynamic professor, we have a, he's too dynamic. So what is the meaning of the dynamic? Unique, exactly opposite. Yeah, so dynamic weather means that changing too much. Dynamic professor, today happy, tomorrow angry. Okay? So dynamic atmosphere, it means that, you know, you can find lots of people are talking together, but you can also find some place that people are studying, some people are actually listening music, so you see that all people. So this means changing. Dynamic model of the system means that to see what changes and what is the impacts to increase or to reduce these changes. So in the model that we develop here, the only dynamic part is current, because d I to dt means the change of the current subjected to the time. Okay? So the dynamic model, this equation is exactly that one. This one. So calculating the dynamic model was not hard. It's very straightforward, easy. And if someone said that I cannot actually calculate the dynamic model of the system, salute. Yeah. Then seems that he or she is not listening to this one. And then probably is a pity that said that, you know, I went to the class, but I was not in that atmosphere, and then I didn't get it, and so I cannot digest it now. So it is very easy. It seems a lots of equation, but doesn't provide something complicated. So now get back again to this dynamic model of the grid connected system. So can you find anything which impact the operation of this system, this model, grid connected converter, or this model, or whatever we have, that we cannot see its impact in this equation? So assuming that if you change the L, you see the current is changing. So let's get back to this. We have switching, we have R, L, voltage in the grid. So if the load change, voltage is changing. If grid something happen, the voltage is changing, and then we have the current. So neutral point, everything we have. So if we get back to see that any of these parameter or variable change, the current injected from converter to the grid will be subjected to this change. Okay? So what is the mission of the grid connected converter? We are going to provide electricity injecting current to support the grid. Okay? So it can be part of the active power or reactive power. So when we are controlling the voltage and frequency, in fact, we are going to play with the current injecting from the renewable energies or storage devices to the power grid. Am I right, Rakesh? Good. So now we have this, and any things happening in the network, we can see. So it's like a tailorman now has the information about your size, and if you see, I mean, you order your pants and return back after 1 month to take it, then if you increase your size, it is not, so it is subjected to your increment. So anything happening here, you can see you have in this dynamic model. Then getting back again to make it more simple. So this is di to dt. This is R over to Li minus V1M. 1M is voltage of the converter here, 1M. So it is like a S times 2 V, VDC. So we go here and put S1 VDC in the state of V1M. Do you agree? Okay, good. When we say that S1 means the switching of the first leg, is not the switching of transistor 1. So it can be upper or lower, doesn't matter, but this is something to say that what is the output voltage. So S1 VDC, and then we have here VMN, but we said that VMN is equal to minus V1M, so it can be S1 VDC, S2 VDC, S3 VDC over to 3. So if you go here, we replace this one, which is S1 VDC, S2 VDC. So we have a SVDC here. SVDC. Do you agree? Okay. So, and then we have actually this V1 over L, so V1 over L. And now we see something a little bit easy, but still we can make it more easier. So just we have VDC here, we have VDC here, so we try to transfer this part to there. So if you get back to C, look, we have this. Yeah, it is not complicated. Yeah, Rakesh? What is the friend name? Yes. Okay, is it clear? Yeah. How many switching do we have? 3. Why? We have 6 switch. Oh, 3 legs. Okay. Okay. So you're thinking about that one, yeah? You're not sleeping. Okay, good, good. I mean, the problem with my teaching is like this one. Always I interact with the student and don't let them to sleep. Okay, so we have D1, the current changes in phase 1 is equal to R over L times through I1, and this is the switching, and this is VDC, so also we have 3 phase, we write in a single phase, yeah? Is it hard to reach to this equation? It's very straightforward. So if later they change anything, you can also follow this structure and also reach to similar equation. So when you go to read some research paper, you see that they have a lots of equation. At the end, it's nothing. If you follow this routine, all of them actually following the same routine. So it is not somehow complicated. Then you can easily understand the paper if you know what is the routine of the actually this calculation. So if I'm going to actually use this one, then I said that it is better that we call this one, because this is switch, we call it DN car. So it means that we call it switching state function, okay? So it means that the switching, the operation of the phase 1 is also subjected in phase 2 and 3. Because we have actually SM, which SM is from 1 to 3. And you see that in phase 2, the dynamic change of the current or injected current from the converter in phase 2 is also subjected to phase 1 and 3. And in phase 3, it's also have interaction with phase 1 and 2. Okay? So, we call it a switching state function, and we make it even more easy by replacing in the same equation. And if you put just a different value for previous this one, so D1 car is S1 minus S1 plus S2 plus S3 over 2 3 S DN2 is S2 minus 1 over 3, and S3 is S3 minus D3, N3 is D3 car is it's like this. N1, N2, N3 is 1 over 3, 2 minus 1 S1 minus 1. Do you want me to calculate it? You show it, or it's clear? This is completely, yeah. So, now we have a system with switching state function. So now R is a constant value because it's the parameter. L is the constant value. Where DC is the constant value. And we have ICA is the injected current from converter to the grid. and also VK, which is the voltage of the point of common coupling. So the point that converter is connected to the grid. So if voltage change, we see that the current change also, and if L we change it, we can also probably you can see that the voltage change is reducing when we increase the L, but we cannot increase as much as we want. And if we consider also the voltage changes in the grid, it means that the fluctuation will be too high. And if we have a smaller value for the VDC, in fact, we have more fluctuation in the output current of the system. So then return back again to this equation replaced by switching state function. And for the three-phase system I1, I2, I3, we can put minus R over L times to this matrix times to I1, I2, I3. So it's somehow just repeating the same in the matrix. But here we mentioned also the switching state function we obtained from here. And V1, V2, V3 is the voltage of a common coupling that we connect the converter to that one. Is it clear up to here? Do you see that you can be an engineer later which working or have an expert in the control of the converter? Yes? You can be? Yes, okay. Shifting the mood is that much easy. Yeah? It's really, it's nothing complicated. You can go be like a prophet of the grid converter control, but the basic is a very straightforward.
Actually, before coming to this seminar, actually I was thinking that this will be very difficult.
Yes. I had the same feeling actually. But now my feeling changed actually. Arya is not here, so tell him at least it was the biggest lose of your life, because you cannot be expert in this for the rest of your life. Yeah, okay. Is here? Yeah.
Current is dynamic in nature, and VDC is voltage across capacitor.
Mm-hmm. No, it is not the capacitor. We have this one, but we have the voltage regulator there. So it can be basically if we have we can have the capacitor, but then the problem with the capacitor is that we charge and discharge it fast. But basically for this type of technology, we use for example, lithium-ion battery, but lithium-ion battery is not fast enough. Then we have also capacitor for the transient, actually, fast transient application for the short time. Okay, but can you, yeah, you can continue. We use, but not for the continuous operation, for the starting operation. So because in some cases, for the dynamic operation, because then if we need the fast dynamic reaction, then capacitor is reacting fine. But the problem is that when we have big changes, then the energy can be actually discharged for the system is not enough to have a big impacts on the stability of the network. Yeah, this is the problem. So you had something to say, I forgot. What? He's not feeling well. Yeah, he was up to midnight in the street. So if I had the same actually experience, I was not feeling well. Yeah. Last night he was too active. So probably this is the reason. Yeah, he's hyper. Okay. So we can buy like a chips and this yogurt. Go to say hello to him. Yeah. So he's in the dormitory or in hotel or somewhere else. Yeah. He's lying. Tell him I said he's lying. Yeah. I had the same actually trick when I was not in the mood to go to class. I said my mom like, okay, I'm feeling bad, headache, this type of things. Yeah. Okay. So, you see that, I mean, this is not that much complicated, but this is the first. It's like you learn how to turn on your car and just drive. If you're going to be rally driver like a Schumacher, then you can go faster actually. So for this reason, but I can say that, you know, for any of the controller, you should start from here. So now we have the dynamic equation of the system. So we see that, you know, we see in lots of book, papers, and then they have such equation, but you don't know from where it's coming. But now we see that we know from where it's coming. So we have a three-phase system. Three-phase system is a balance, so we make it more easier, and then just the I1 plus I2 is equal to minus I3, or V1 plus V2 plus V3 is equal to 0. So by this we can easily remove this part because they are balanced system, and to reach this equation. So we call it dynamic model of the system. Now is a starting point to design the controller. So at the beginning of the class, I mentioned that to draw an appropriate plan to control the interface converter for integration of energy source into the power grid, a dynamic analytical model of the proposed model should be developed. Now we developed it. We have the dynamic model of the system. So just one probably comment is that, you know, this is the dynamic model of such a system. So then in some cases, instead of RL filter, you can use the LCL filter, you can use the different types of the actual filter, but it doesn't provide anything. You can just add some equation more and then follow the same thing and reach the same, a little bit different, but at the end you have DI and something like this, and just you had some capacitor, and that's all. Okay, it shouldn't be that much complicated, but I remember that, you know, I used this one in this paper, a control technique for integration of DG unit to the electrical network, IEEE transaction in industrial electronics in 2013. I use it, it works very well, and then I implemented by hardware, so it provided a really good answer. THT was less than 5%, it was 2 point something, and it works very well. So if you don't have any strong reason, then you can use the same. But there is one thing that, you know, for the very high power or very low power, the types of the filter can be different. So it is not applicable for all level of the power. So basically, this type of technology filter actually is more feasible for the medium power. Yeah. So, Siddhant, if I put the LCL filter, you can make the calculation, yeah? Yes. Can you come to do it? You can try no. You said yes, without hesitation. Okay? So, probably we can just see what is happening. So we have a converter, V1M, and we have R, L, C, L, V1. So L1, L2, C, you can neglect this R. Can you make the KVL and KCL for this one? Yes or no? Yes. Okay. It's that much easy. But just you add the C here. Okay? It doesn't provide, so you have also IC, so I converter, I grid. So I converter is IC plus IG. Then you make your KVL. That's all. And you can actually use this one CdV to dt for the current. Okay? So it is not that much hard, and don't make everything complicated. You see, wow, it was different. I talk in RL, now it's LCL, and so, yes? VDC? No, DC link voltage, yeah. It's like a, so assuming that you have a wind, we shown yesterday. Yes. Where is the, okay. Yes, it's here. Yeah, it is, look, basically, so assuming that we have any power, okay, so it is like this, okay, this is the power. Can you see it? This, okay, so it's like a power of wind, okay. Then we apply to this, for example, capacitor. Okay. Then we have this one, I, which is CdV to dt. Okay. Then we have P also, VI. Okay. So then V is equal to P over 2I. But the problem is that this V is not regulated. So for this reason, we need the regulation, voltage regulator here, which can be also based on the extra DC-DC converter, adding in the DC side, or probably you can actually use the, somehow we said that, for example, the VDC we need is 600 volt, but we have actually some fluctuation. Then in the voltage of the DC, so we said that reference voltage is 600, but the voltage that we have is VDC is not 600. So we have some problem here. Then the compensation by PI controller is needed, and then you have actually some equation which create a ID for VDC. This ID for VDC can be added to the control loop of the current, and after transient time we reach the DC value, regulated DC value for the DC side. So let me show you in a real case. Yeah, this is a real case in simulation. We had 800 volt, but it was the input voltage that we had from the input power from the wind. and then we provide actually regulation for the control of the DC. Then after this transient time, you see, this transient time, it reached to the constant DC value. So basically, there are some method, but it depended that how much your system is sensitive. You can basically say that I can inject the power to a storage, and then a storage can be used as a DC part of the converter and use it. So, for example, this type of transient cannot be used for the sensitive load, but or in some cases that it is not that much. For example, for a residential building, it doesn't provide any problem for the loads. So you can use such a technology by regulating the DC voltage. But you consider that this is very unregulated power, because we have also controller in the speed of the blade, so it cannot go very deep to very high. So, any questions so far? So up to now, we get the idea about the grid forming, grid following, and grid connected converter, and also dynamic model of the system, how we can create it. So now, Costa, am I right? We get we discussed this during today, yeah? So what is the meaning of grid forming converter? You were absent. Okay, so so we discussed, but you were absent. Yeah. Anyway, we will discuss again, okay? Don't worry. So now we reach to the dynamic model of the system. So what is the benefit of this model? Udaya, do you have any idea what is the benefit? Exactly, yeah. We need it for the design the controller. So we discussed about the part transformation. We said that if we transfer the system from ABC to DQ, then we can make the controller easier and more flexible. You can actually use for different applications. So now I'm going to transfer this three-phase system to part transformation to see that, is it really true that if we transfer this one from ABC to ODQ, then it makes our life much more easier if we are going to design the controller or not. So, so for this case, we get back to the part transformation system we design here. We discuss about this one, and we see that we can use this matrix for the DQ or for the reverse one. So now we are going to get back to dynamic model we obtain for the system, and then this one, and transfer it to DQ. So if we get back for three-phase definition we had, it was like this. di to dt is equal to minus r over to l I ka minus 1 over L dn ka VDC plus V ka over to L. Okay? Now we are going to actually transfer it to three-phase. So, does anybody know that how we can go from ABC to DQ? Part transformation, but how? We should transfer all of them one by one. So for the first phase, so this is something that we have from the matrix. So first phase is the cosine omega t times to ud minus sine omega t times to UQ plus 1 times 2 U0. So U can be actually voltage or current, doesn't matter. Or, I don't know, switching state function, anything you want to transfer. And U2 is also the same, U3 is the same. So, we start by first phase. From here, so it is also very easy, but if you don't pay attention 100%, you will not get the point very well. So, based on the equation, this matrix U1 is equal to UD cosine omega t minus UQ sine omega t sine omega t plus 0. Okay? Do you agree? And what is the omega t? Angle of frequency. I need a complete answer. What? Page? Page of what? Omega t. What is the omega t? Okay, but from where? From where? From where is coming? I mean, assuming that I'm going to program this one. No. No. Between V and D, normally we have 90 degrees. It's constant. No, but what is the omega t? You can say that this is 2pft. You can see that this is the, I don't know, frequency of the sky. You can see, but give me complete answer. And give me the reason for that one. Angle of what? Okay, you say, but you don't give the complete answer. Yes.
Omega is the angular frequency of the
Great. Okay.
Omega is the angular frequency of the voltage or current, whatever we are using. And
Okay.
T is the time that we have.
No. My question is that what is omega t? But from where is coming? I know that, but this angle is coming from where? From where? PLL. PLL measured something and then give the omega t. Okay? So this something is coming from where? From grid. I mean, no, it's coming from grid. Yeah, because we are going to synchronize with the grid. So if we put this one, omega t, from somewhere else, it means that we are transferring our dynamic model to the angle of something else. Okay, so we are going to be integrated from the grid. So if we get back to here, to this model, we get V1, V2, V3 as the input to PLL. Then we get the omega t as the output. Then this omega t from the grid is used for the control design. Why? Because we are going to be synchronized with the grid. It means that when we provide the current or voltage actually for the grid, it should be synchronized to support the grid. And if we don't consider that one, it makes a disturbance. Your converter actually react as a source of pollution, not a source of actually energy for provision of the supportive functionality for the grid. So this is the problem, and this is very important that you consider any omega t you consider for this Park transformation, transfer your dynamic model to that atmosphere. Okay, so it is very important you consider this one seriously. So then we get back to again to U1. From here, this matrix, we have U1 is cosine omega t, ud times the cosine omega t minus uq times the sinus omega t plus u0. So now our u can be ICA. Do you like it? Because we can transfer all of these things. So L is a constant value. So we don't need, we just multiply multiply it by di to dt. So we don't need to convert it. But di to dt is, and IK is, dnk is, vdc is not, vk is needed to change because they are a variable, they are not constant. So then now for the U2 and U3 also we follow this ud times to cosine omega t minus 120 degree, uq times to minus sine omega t, and we see that we have also 3 equations here for that. Okay? I forgot your name again. Krudika. Okay. We have 2 problems. One is a hard name for me, and then you are actually Krudika, like this. Krudika, you are sleepy, yeah? Yeah. Is it boring for you? Is it boring for you? You feel sleepy? Ah, you were the same team with them, so you didn't sleep well. Okay, good. If you want, if you get tired, we can stop it here. But if you, Udaya, should I continue or continue? Okay. So now in phase 1, L di to dt plus Ri plus dn vdc is equal to V1. So L di to dt, L di to dt. L is constant, di to dt. Di is cosine omega t minus iq sine omega t plus I0. Okay? We wrote based on the I. It was U, now is I. So, di to dt. So is d to dt cosine omega t minus id omega sine omega t. Do you agree for this? Yeah. F times to jt is f prime g plus g prime f. Okay? So this is this part. Okay? And then we have another part, minus. So f diq to dt sine omega t minus iq omega cosine omega t. So is this part. And plus di0 to dt. Is it clear? Yeah. So the first part we have also L di to dt. So L di to dt. L and L. It covers all. Yeah? So, second part, Ri. R times 2. ID cosine omega t minus IQ sine omega t plus I0. Yeah? Is this part. So now we cover this part and this part. And we now is in dn1 VDC. VDC is a constant value. So, but we consider dn is equal to dn1 is d cosine omega t or dnd minus dnq sine omega t plus dn0. Okay? So we had VDC times 2 VDC. Yeah? Siddhant? Is it still clear or? Yes? Okay, good. Thanks for confirmation. So we have also here, and then now we jump to V. V1 is equal to Vd cosine omega t minus Vq sine omega t plus V0. Okay? So look at here. We have this part. Is it like this? This part is this. This part is this. And equal to this part. Okay? So, Rakesh, is clear for you? What are you writing? But I give the slide to you. Okay? So this material also I sent to Udaya and can share with you. Okay. So any questions so far? No. Easy like a piece of cake. Okay, good. What?
In some cases, we are going to consider V0 is 0. VD, VQ and V0. V0 is 0. But here we can consider it as a 0 or in unbalanced system.
I mean, basically, if this depend on what kind of actually system do you have, but we mentioned because this is the balance system, we can actually ignore that one.
If it is unbalanced, how we are going to calculate?
I mean, the unbalance, just we return back again for the first assumption from here. If you notice, we said that this is the balance system, okay? But when we have unbalanced system, then we don't consider this one as a 0. It doesn't provide something, especially when you're programming the MATLAB. You just can say that, okay, this is I1, I2, I3, and when you provide the input, it calculated based on that one. So it doesn't provide something, but you cannot assume that this is the 0.
Only it is 0 in unbalanced.
Yes, yeah. Because I mean, if you don't understand the balance system, then unbalance is more complicated, and the equation will be 10 times more. But when you go from the actually coding the controller by MATLAB, because you just write it and see the result, so it is not that much hard. But the important thing is that when you make the programming, you should at least have an idea about that, what is the shape of the signal you are expecting. So for example, in my case, when I'm using the simulation, I don't use PLL. I don't like it. I just calculate the alpha beta and based on that get the inverse tangent and then said that if the VD is in direction of the V reference, VQ is equal to 0. And then I put a scope. And if VD is DC and VQ is equal to 0, I said that, okay, now nobody can say that this is a problem, because it is impossible. If you program it the wrong way, the Q will be 0. So then immediately when run the actually code, I see actually the VQ is 0. It means that up to here my simulation is correct. So you should have actually some idea about the stages that you are proceeding. And the worst or biggest mistake is happening, especially for the PhD student. They start at the beginning. They are going to close the simulation and run it and to see that it works well or not. No, it is the biggest mistake. So you should be like a doctor. When doctor, someone has a good experience, you go there and see that, okay, I have a headache. Then less experienced doctor said that, okay, headache can happening because of the flu, can happening because of the corona, can happening because of the, I don't know, sign problem, can happening because of someone hit your head. And then let's try, okay, go to take a photo of actually your, I don't know, what do you say? Then you see that, okay, your head is not broken, so it is not. Then have a corona test, then it is not negative, so it is not good. Also, again, go do this one. But the experience, doctor said, okay, so let me touch your, okay, so it is because of this, and go do this one. Okay, so you should be like this one, because the expectation from you is that at the end of your study, you should find the solution based on the result you see. And if, for example, you see the graph is not, the injected current is not actually pure sinusoidal, you can easily say that, okay, it can be because of the, I don't know, DC voltage is not regulated, or switching frequency is not tuned well, or the filter is not designed well. So these three factors can be the reason for this THD. That's all. So for this case, the expectation from you is that, you know, when you make the simulation, at least you don't close your eyes and say, okay, so finalize, and then it doesn't work. I mean, the chance is then less than 1% if you make a simulation and then say that it works very well. Even less than 1%. Do you agree, guys? Okay, good. So, now we get back again to DQ. So we have this equation. At the end of the story, we have L di to dt Ri plus dnvdc equal to Vd in dq0 reference actually transfer function. So this is for phase 1. For phase 2, we have also the same scenario, but with 120-degree phase shift. So again, we follow the same, and when we actually repeat the same procedure, we reach to this equation. But the only difference from phase 1 and phase 2 is that in phase 2, we follow this one, cosine omega t minus 120 degree minus, it has the phase shift. So for this, the new equation will be obtained almost similar, but with 120 degree phase shift from the phase A. So at the end of the story, you have this equation L di to dt plus Ri plus dn phase 2 times to vdc equal to v grid in phase B or second phase. And in phase 3, we follow this part. Cosine omega t plus 2 pi over 3 times to Vd minus sine omega t plus 2 pi over omega t times to Vq and plus u0. So by this, we reach to this equation. Okay? So it seems a lots of equation, but you know, we are not mathematician, we are engineer, and then we are very smart, intelligent person that that can easily calculate this one, but we have a software, so easily we can use the software and calculate this one. So we don't need to memorize this one. So at the end, if you have something similar in your exam, it will be very probably a stupid question in the exam that the expectation was that you memorize the Park transformation. I mean, I'm teaching this course or using this Park transformation several years, but still I cannot memorize it. Yeah. Udaya, can you memorize it? Okay. So, you want to close it? Now, let's conclude this part and then we, okay. So now we get back, actually we have 3 phases, and in phase we have phase 1, phase 2, phase 3, we transfer from ABC to ODQ or DQ0. So by this assumption, we make the summation of the actually 3 equations. Phase 1, equation 14, phase 2, equation 15, phase 3, equation 16. So by summing this, you can see that, you know, at the end, we have L dId to dt minus L omega iq plus RId plus dN dV dc minus Vd times 2 cosine omega t minus 2 p over 3 plus cosine omega t plus 2 pi over 3, okay? And then in the second part, L di to dt in q axis. It is in d axis, is in q axis times to sine, and at the end also for the homopolar value we have this. So if we get back to this, it is equal to 0. When does it happening? It's happening when this value is equal to 0, this value equal to 0, this value equal to 0. So L di to dt minus L omega iq plus Ri d plus dN dV dc minus Vd equal to 0, this part. And this part also equal to 0, and this part equal to 0. So the summation of these 3 phases will be equal to 0. Is it clear up to here? So what is happening? You see this equation change from ABC to DQ. So we transferred from the ABC operating condition to DQ condition. So if we get back and see a little bit with more detail, we see that we have L dId to dt minus L omega iq plus Rid plus we see that all actually components here are from D except this part. And we have also the same, all components are Q except this part. And we call it coupling, actually point of this system. So it, yeah, cross coupling. And is it good or bad? It's bad. Why? So, for example, we are going to control a converter. and I'm saying that I'm going to inject 10 kilowatt active power, and later see that active power can be modeled by ID, reactive power can be modeled by IQ. So it means that I'm going to inject 10 or 20 kilowatt active power in time t equal to 3 seconds. And then, so when we have this power increment, in fact, we changed the ID, but this ID appeared in I here in the Q-axis. But Q-axis also refer to the reactive power. So you see that, reactive power is 0, 0, but when you have this, we have a spike here. Okay? So for this case, we should remove or find a solution to remove this part, and we say that decoupling. Okay? So, does anybody has any idea about this? How we make the decoupling? Or are you interested to know how we make the decoupling? Yes? We see later, okay? So I'm now getting tired, so we can take a rest and then follow with the Udaya afternoon. Coupling, continuum what? Tomorrow? Okay, tomorrow. Yes. But we will get back again to a little bit explain to other people that were absent tomorrow. Yeah.
We can wait for lunch, we'll wait for the lunch, and the lunch can be served in the ground, the same location. We can collect it. In the afternoon session, I'm going to handle the session on technologies for the renewable energy.
Yeah. But before leave, is it actually understandable or not? If you have some problem, tell me, okay? Because this is very important, and end of the, we follow the same actually direction up to end of the next week. So if you don't understand these things, just tell me. But I'm saying that, you are very intelligent and you can understand it very well. Yeah.
One material, is it there with you?
Yes.
Okay. And lecture schedule?
Yeah. Just give me 1 second.
Yeah. 1, 2, 3. It's fine. You get the voice? Okay, fine. Yeah. Yeah. Good afternoon to one and all. So first of all, I'm thankful for giving the opportunity for delivering the lecture on this energy storage technologies for the renewable energy sources. As you know that now we are entering into the storage technologies. So first and foremost that why we need to have the storage system. You are getting the brief overview regarding this storage technologies, and that the storage is an important contribution for your renewable energy sources. Because most of them that you want to dependent on the is it fine? Okay. So you want to dependent on the renewable energy sources, and you want to make use of exploration further about this renewable energy sources, especially on means like that the focus is going to be on wind energy system or of solar energy system. These are of that the stochastic in nature, that they won't generate the constant power, constant output, that we will not get the constant. But what we are going to say that always that is the load is the master, source is the follower. we want to make it means whatever the disturbances at the source side, it should not reflect those disturbances at the load side. Otherwise, you know that what will be the consequences if the sources are not following to the requirement of the load. What will be the consequence that you will experience? Suppose that if you are taking the induction machine, either can be of AC machine or it can be of a DC machine. Okay, if the quality of the power is not good enough, so what will be the consequences? Can anyone of you? What? Oh, sorry. What will be the consequence if the power is not good enough to feed to either AC machine or of a DC machine? What will happen? And our loads are of which are of non-linear in nature. Most of the loads which are of non-linear in nature. Mm-hmm. Yeah. Yes, exactly what you are saying. Means like the rise of the temperature which is going to take place and the performance of the machine is going to come down, and it is going to be, we will not, if you see the our lights itself, if it is of a flickering, we feel that it is of uncomfortable to the means that the people are of those who are working in the lighting area. Yeah, and then mind also there will be stress across your mind, and but you know it is more that you are means like swimming in the distributed energy sources, and you want to make it to promote in a bigger level, and then this the generation is okay during the peak timings or of when sunshine is there, that you can generate the more power, and then if it wind flow is more, that you can generate the more power. But during the night times or when the wind flow is not available, what you are going to do, that we can't shut down our loads or we can't shut down our office. Means like to increase, means like if you take the cases of some kind of industry, that the production also supposed to be maximized by using proper kind of power supply or of proper illumination, that it should be that the production can be maximized. How it can be made it possible? Okay, if the wind flow is not there, sunshine is not there, then obviously that you require to have the storage system. Okay, storage system is of mandatory. There are wide variety of storage system that we can talk. That the storage can be, yeah, as you know that you have the two types of power, AC power and DC power. Yes, and the AC, as you are obviously that you say that AC can't be stored. DC only, that is the only source that we can store the energy for long time, and it can be reused for your means for your application part. So in this DC also, as a means like what it is a kind of, after all it is a storage device. Means like what as a electrical engineer or of either power system, power electronics, or of some illumination engineering, what is their role to for this kind of storage technologies? Means like they will say that the chemicals, it is my profession, and then metallurgy, they will say that it is their profession, as a battery or of some kind of fuel cell, and it is manufacturing will go to that side. As an electrical engineer, what is our role? Means like you know, as a power electronics, power system, this thing. But as a power electronics or of a power system plays a vital role. Okay, what is that role? Can any one of you, can you guess what we are going to have the discussion in this one? How the means like as a electrical engineer are going to support for the energy storage technologies. Energy storage technologies. That you are injecting power to the grid, extracting the power from the grid. Okay. Then how you are injecting the power to the grid? You are means like that you are injecting the power, means like either PV from PV side or of wind energy side, that you are trying to inject the power to the conventional grid. How? Means like you are going to make use of conversion. Yes, either you are going to make the frequency match as well as the magnitude match, then you will inject the power into the existing grid. By making what we can say that injection, it is of a somewhat you are going to make use of a kind of a converter, then match the frequency and the voltage magnitude, then you will inject and make your bit more stronger and stronger, okay, without dependent on the conventional part, and you will inject. That is well and good. You want to make it more stronger. Here also, that if you want to, that your storage systems also wants to make you to be more stronger. I can store. I will there are you are hearing something like batteries. You are hearing flywheel energy storage systems that you are hearing. Some kind of I posed the things superconducting magnetic energy storage system. Even the electrolytic capacitors, okay, and also electrolytic capacitor, pumped energy storage systems. These are wide storage devices which are available. So then what we are going to do? Is there any role of the electrical engineers in this thing? That batteries, what is the role as the electrical engineers? Power fluctuations. Yeah. You know, any one of you, if you talk about this mathematical modeling, that you are aware about the mathematical modeling of your power batteries. Have you come across battery modeling, and then this kind of flywheel energy storage systems are of supercapacitors part? Yes, and they will say that it is not come to your arena. Is it so? No, it will be under the part of the electrical engineers. Even though that the first the statement, what we can say that we are the when I talk about the batteries, means I want to go depth about the the different types of batteries. Means like you have the lithium ion, nickel cadmium, lead acid batteries, and some hydrogen batteries, that you are having the everything. That you know the good at fundamentals, I mean to say that. Okay, what's the best characteristic that you are aware that batteries are good for are having the good energy density? Yeah, yes, and that characteristic that we are going to exploit for our application part. So this characteristic good enough, means we can say that. Then apart from this one, I want to know more about the thing about the electrical engineering contribution in this storage technologies. Can you guess what supposed to be contributed to the energy storage technologies? If I talk about this thing, initially my students also, they were reluctant to do this topic, and it is not good enough to have more contribution to the this renewable energy sources. Is it so? Energy storage is a good contribution, or means like a bad contribution? Good contribution in which kind of sense? Improvising the potential part. Yeah, okay. Reliability, efficiency, then stabilizing the system, okay. Grid optimization, yeah. Reliability, stability, grid optimization, efficiency, these are the contributing factors for enhancing your system. Yes, how you are going to achieve all these things? That the next, that the fundamental question, how you want to achieve the things? Yeah, technology, we can say that it is a wide, the definition is so big for the technology. Here,
when we are going to meet the requirement, any condition, we have that much of energy with us.
okay,
We can stabilize the system very quickly.
yeah, okay, yeah, stable,
To match the requirement
okay.
at any stage.
Yeah, fine, good enough that the stabilization it is done. now I am trying to grab some points relevance to the electrical, means like that towards my entry into the PPT. Mhm. Mm. Okay. Yeah. Mm. Okay. That the chemical engineers will take care about the improvising the energy density about the batteries and some anode or cathode. This development will be. Mm. Mhm. Mm. Uh-huh. How you are proper optimization. Yeah, that the optimization, that what kind of optimization, you know that there are the challenges posed by the batteries, the challenges posed by the other storage system. What are the challenges? Means like each and every system that you can say that we are having the advantages and the disadvantages. Okay, every system is associated with the advantages and the disadvantages. This we will forget about the disadvantages part and focus on the advantages. How we can exploit, means like use those advantages, characteristics of storage system to our system. Okay, means like ours. So then, how now I will come to, after having the discussion, I can say that we'll move to the next level. I mean to say that the power converters are of very essential for the storage devices. Without power converter, there won't be any possibility of storing the energy. That you are talking about the power flow between the grid to the storage system to the grid, or from the grid to the storage to the load point, or from the load to the storage to the grid point. These are, means like, what do you call one way of flowing the power from source to the load, and from the source to the load to the source. First part is from source to the load to the source. What do you call the power flow? Yeah, that the concept is also there, but indirectly I am saying that it is like a source to the load and load to the source. But initially we will talk about the only one way, that is from the source to the load part. Source to the load part, it is of a unidirectional power flow, we call it. And then that again you are having that the power flow from the load to the source side. We will reversal of the power flow. It is like, you know, this is one way of doing the power transfer from one source to the other source, that we will say bidirectional power flow is there. Okay, and also here that the bidirectional power flow is good enough. Then what about sometimes that within the sources they do have fight among themselves, which one has to supposed to be contributed. How you are going to do that thing? Means like, I am big boss, I am having more superpower, I can give the power to the load. Someone says that I am superpower than you, I want to give the power supply to the load, and I am deficient enough, I want to grab from you. Okay, then the power exchange among the storage devices also. How we are going to transfer the storage devices, that the power within the energy elements. Okay, these are the things that we are going to have the discussion in today's class. Okay, and if you can get familiarization that and also that the objectives of the work also, what we are going to have, that we can see that. So now the power electronics equipment plays a vital role for storing the energy as of now. What type of conversion, that the things that we are going to see that. So if you see that the application can be of, now you are having my flow of presentation is going to be like this. Okay, I'll take the, yeah, sorry. Yes. Yeah, this one, that the introduction I will talk about, means here in the introduction I may take an examples of distributed energy sources or of electric vehicles I can take, and the various types of energy storage technology that what we are having. Special focus on this flywheel energy storage system, superconducting magnetic energy storage system, and then supercapacitors, batteries, and this hybrid energy storage system, some kind of bidirectional DC-DC converters, how the power flow is going to be, and then some of the results that I will discuss, and at the end conclusion. So then now it comes to this type of storage technology, means like that the introduction and the review, this thing. None of them, means like they will say that these are of somewhat complicated, that you can't see the real-time applications of this one, still under the maturity level, that the superconducting magnetic energy storage system. Some of the developed countries are working on this kind of SMES devices, still yet to come to the commercialization of this product. And you know that this flywheel energy storage system, it is a mechanical kind of storing the energy, but it well proven technology, that the flywheel energy storage system. And problem, it requires the power electronics equipment as well for this flywheel energy storage system, how it is movement of inertia, that the concept, and the speed of your flywheel also it matters. So then, and then this supercapacitors and the batteries more popular. More popular means earlier, that is more popular is the batteries. Okay. Then the afterwards that they are syncing or means combining with the supercapacitors part. Now you say something about, you are hearing for long time and long days about the batteries, and also that you have the, is there anything that with the batteries that we can proceed also, no? That the batteries, any issues with the battery storage systems? What issues? Okay, life cycle. Okay. Yeah, life cycle of the battery. That is the fundamental reason that you are making use of, where you are making use, that the daily usage of your battery. Yeah, best example is the mobile phones. In the mobile phone that you are making use, for every 6 months that you require to replace the battery. Then what it is happening, that the performance on the first day of your purchase of mobile phone is not the same on the last day of your performance. What it is happening internally?
It is going to consume the electrical energy stored in the battery itself.
Okay, then
some heat is going to produce.
it becomes bulges and try to explode. Leakage or means like you, have you seen the leakage of the battery? Yeah, internal leakage, but external leakage you can't observe. Yeah. Then you will, if the internal leakage is happening, means that the bulging of the battery is going to takes place. Okay, it becomes bulges, and over the means never explode. If it explodes, what will be the consequence? Then it is very dangerous. I mean to say that battery is like a bomb. Okay, and you can't overcharge or means like over discharge also. The optimal usage of the battery. Yeah, 20%. There is some percentage prescribed by the, what we can say, that the manufacturer, according to the manufacturer, that we are going to make use of the batteries part. So that is the only how the means like internal operation is going to happen in the batteries. What kind of thing which is going to happen with the batteries? And even though that this is one problem that you identified and bring it to the notice to us, but still then battery is the more popular. Why it is so? Means like it is popular for distributed energy sources. Yeah, it can store, but there are some problems are there. Okay, that he is saying that internal leakage.
And also the life cycle will reduce after so charge.
Yeah, that how you are going to estimate this kind of process when it is going to change the life cycle, and the performance on first day is not the same on the last day of your battery. So then how you are going to estimate? You require to have state of charge, depth of discharge, and then chemical degradation, right? That the temperature, working condition, yeah, contamination of the anode and the cathode. These things will be there. Blah blah. Means like these are the things that you can. But it is very complex to design the battery model. But simple that the battery models are there in our MATLAB and we do the experimentation. So we can't eliminate completely all these problems, okay, that we'll try to optimize these problems. How we are going to optimize the problems? If you make it, you know that when you are going to take your power semiconductor devices, okay, you have the safe operating area, okay. If yes,
State of charge or temperature, whatever it will be,
okay.
flow of current,
Mm-hmm.
we can optimize.
Yeah, that the state of charge that you will call it means like yeah, this is the thing. When it comes to the semiconductor devices, you have the stress across your switch, voltage stress or current stress. If you increase the stress, what happens? Then the performance will go down. Here also the same thing in the case of this kind of batteries, that it should be optimally utilized. That the professor rightly pointed that we are going to make use of the batteries in the steady state conditions, okay, not in the transient condition. Transient condition, why not in the transient condition? That you will have more fluctuations, okay, that the fluctuation, that the transient period exists for short period. With the short period, it demands more power from the source. That the battery means like you know that you are making me to run at my speed is limited to 10 kilometers per hour. Okay, if you are making me to run for 100 kilometers per hour, it is not possible. Similarly, it is the case with the battery as well. Okay, if you want to take the more power, that it can't. My stability is like this only. I am very arrogant to, I won't react to any of the loads. That is the nature of the battery. Okay, and now when it comes to the one more thing, this is the battery part. Now we'll comes to the supercapacitor part. Okay, in this yes, I can make you to the, I will come supercapacitor part. In this supercapacitor part, what is it different from the electrolytic capacitor? That the supercapacitor. Many people, how many of you are working in this storage technologies? Is there anyone? Yeah, I can understand. It is not yet mature. You know, I got here because of these things only. Okay, I mean to say that it is 20-25 years back. It is there in Europe. Okay, they are making use extensively for their application. Now you say that the supercapacitor, is it different from the conventional electrolytic capacitor, or is it the same? Yes. Is it different or of same from the electrolytic capacitors? Yeah, high power density. Yeah, that I can obviously will say that it is of high power density. What's the internal structure? Means like if you see that the name itself we are calling as a super. Super means like you are superconducting. We are saying some superconductors also that you heard in your studies. Yeah, yeah, obviously, but not completely zero resistance, but milli micro ohms of resistance is present. Okay. Yes, offer less resistance is there. That is one. If resistance is lower, then what is the advantage? Losses will be reduced. Okay, we can pass more current through it. Okay, and with thin wire, that we can more hundreds of amperes of the current through that thing. Yeah. Here in the case of the conventional electrolytic capacitor and the supercapacitor, the basic difference is that the presence of dielectric medium. Okay. In electrolytic capacitor, you will find the dielectric material C equal to epsilon naught A by D. Okay. That the area is going to be more in the case of electrolytic capacitor. In the case of supercapacitor, this dielectric medium is absent. That you will have the capacitance is proportional to the area of the surface. Okay. Then you will have the wider area. Now at the maximum for your transmission, distribution in power system domain, that the capacitance, electrolytic capacitance at the maximum, that you will find the millifarads. Okay. You can't get more than that, millifarads, hundreds of thousand of millifarads that you can. But in the case of supercapacitor, it is in terms of the farads. Okay, 58 farads, 58 farads is of, we are working on that. Okay, that is the one beauty of the capacitance. But the problem is there, that the electrolytic capacitors are rated for your line voltages, but the supercapacitor is not so. That the rating is very. And another problem also will be there. And every system that I am saying that it is associated with the advantages and the disadvantages of the system. Okay, that will take the positive aspect and forget about the negative aspects of it. And my as a power electronics, power system engineer, electrical. Basically, I will talk about the electrical engineer. What is our role? This is the manufacturing side, and physicist will say that will manufacture, and what is your role? And then chemistry, they will come, and it is my role, we will manufacture. Then what is our role? That the usage, optimal usage, how we are going to control the charge and the discharge cycle, state of the charge, depth of the discharge, and how we are going to optimally usage the contribution of the power level by the supercapacitor at the required circumstances. That can be dealt by the power electronics engineer. And the power flow also, that you are telling about this, the concept like vehicle to grid, grid to the vehicle concepts. Okay, almost all the electric vehicles are fitted with the batteries, and then you want to harness the energy from the sun, or from the sun only. Then you require to store it. That the storage. Another thing also that I want to say that that the electric vehicle usage. Is it the same that during your starting condition and at running at the rated speed, that the vehicle is going to consume the same amount of power? Starting condition and during scheduled speed or of rated speed, does it consume the same amount of power? Starting is high because it is going to drag. Huh? Yes, to overcome means to start from the 0 kilometers to the up to 60 kilometers per hour, like that. It is takes more amount of current from the source part. And if you then after reaching it, just to maintain the speed, we have to maintain the voltage level. Okay, for that battery will come and support that part. But during from starting from the rest portion, that you require the huge amount of current from the source side. That can be delivered. Battery, we will say that it can't be delivered, and that's the reason that the speed of your vehicles are of, what's the speed of the vehicle, electric vehicle speed, maximum speed? 25 kilometers. Okay, you can't go behind that thing. And now these people are there, European and Americans, they will have the mature technology. Then they are working on this thing and they are making the speed 150 kilometers per hour and the 200 kilometers per hour. So that understand. Then if we have this kind of technology, something like hybridization, that initial transient can be taken care by your some other source, then we can enhance the speed of the vehicle. Okay, this is what that we can see. So now, actually, I will enter into the topic. So this is the introduction about the introduction about the DC microgrid architecture and the special focus. All the time means we are focusing mostly on the DC microgrid structure. Okay, all your electric vehicle means this DC microgrid. Why we are focusing is that the energy storage is going to happen in the form of DC only. With that intention, that we are making use of the DC microgrid for our application. So electric vehicles are promising alternative to the conventional vehicles to their environmental friendliness and higher efficiency. You want to means working that the theme of the GIAN course also to reduce the carbon emissions, net zero concept, to reduce the losses. This one, even though electric vehicles came to the market, they face lot of challenges in replacing the IC engines. Still today, complete electric vehicles run with the electricity. We can't see that in association with the IC engine that we are seeing that. And then pollution caused by IC vehicles are one of the important regional global warming, ozone degradation. So every countries are pushing themselves to sustainability. Even our mission of our government also to promote more and more electric vehicles to the market, and they are giving the subsidization on this electric vehicle to make them the people habituate to the usage of the electric vehicles. Then environmental impact of electricity sector led to the widespread usage of the renewable energy sources, especially means this one also what we can say associated with that everyone that you are making use of the rooftop solar power generation and small windmills, means wind is not that much I can see that in our region, but the solar self-sustained one means government is providing the subsidy for installing the rooftop solar plantation. That is, and it requires anything that if you take this one without storage, we can't imagine the sustenance of the system. Without storage, that we can't imagine that the sustenance of this kind of system. So we require the storage. Without storage, you can't imagine this distributed energy sources. These are of stochastic in nature. Then our system also will collapse. Then stochastic behavior of the renewable energy sources, many issues with the stability, reliability and the power quality. The issue of uncertainty with the renewable energy sources can be addressed by integrating with the energy storage technology. That we are going to have the things on it. So this is the complete DC microgrid, generalized DC microgrid architecture, that we have the different types of distributed energy sources. If you take the fuel cells, battery also can be considered, supercapacitor energy storage system, and then micro, hydro, electric power plants, PV plants, wind plants, and the terminal to AC grids. And some of the applications, what we can say that basically that the first part will be the electric vehicles charging infrastructure development. Here also when it comes to the electric vehicle charging infrastructure development, you can charge your electric vehicle by taking the home power supply. So then what it is going to happen? Can we charge with your household power to charge your vehicle? Yes, of course, we can charge. After all, it is electricity only. Then we can charge from our house also. But why specifically you require the charging stations?
Large amount of current at that time. Because of that, the voltage fluctuations will occur around the area.
Okay, fine. Then there will be a dedicated substation for you to charge your fleet, hundreds of vehicles. That there will be a dedicated substation, you can charge the things. It doesn't mind. Okay, I will give the separate power supplies to you. you can charge the vehicle. Then what's the advantage of means like household? My question is that in this way that from house also that you can charge your vehicle, or from the means a separate charging infrastructure that I want to have for this one. What is the motto of establishing the time? Time is one factor. Yeah. Means the time in the sense that if you increase the current rating, obviously that the charging is going to come down. That is the intention of having the high current, means like that the type of power supply is going to be like this: high current, low voltage power supply. Okay. If you are having some kind of a booster kind of things will be there. That power supply in the nature of what high current and the low voltage, that it is going to charge it so quickly in fraction of minutes. And the customer, they can't wait for hours together. If you charge with your houses, means it may take 8 to 10 hours time period to get fully charged about your battery span. So that high current, sophisticated cables, connector, there are standards of the connectors are required to charge your vehicles. That can be done with the charging infrastructure. This is what that the government is promoting to have. And then industries, you want to increase the some production, means like increase the production, that you are going to make use of the storage system. And then hospital, these are of sensitive loads, that we can say that. In the during the mid of your operation, if power goes, then what is the fate on the human body? Yeah? Huh? That we can imagine that these are of critical loads. I can say that hospitals, domestic users for cooking and maintaining hygienic condition that you require, and the residential apartments to avoid the, means like many issues will be there that you can see that. And then data center, and we want to maintain the continuity of the power supply to your data centers. Yeah, fine. So I am not that much active to make you to be alert in the class, and be attentive for the class. And some of them, they are, it is like a lullaby for them, my class. I don't want to make you to be a lullaby for you and be active. Then the next portion. This is the standard structure block diagram that I am projected here, means for your electric vehicles part, I have focused the main thing, that here battery part, supercapacitor part, and the second block is associated with the bidirectional DC-DC converter, and it is going to take care of the DC bus and the dynamics associated with the DC bus. And then it will be given to the next level, that is the inverter. From inverter, that will be the AC machine. Or here without inverter, that we can have a standard DC machines also, we will avoid this stage. If you are going to have the more stages, what will be the thing, that the more losses will be there. And here we are mentioning the power flow between the, means what, battery to the this bidirectional converter, or from the bidirectional to the this one. And also this one, that we are going to have some kind of braking part. You are aware that there are different types of braking, that the regenerative braking part will be there, and dynamic braking is there, rheostatic braking will be there. You want to save the energy, okay? By having this kind of architecture, means like we can recover the energy during brake period. Brake period means like what? You have the road condition can be up or down, or it can be of zigzag conditions will be there. Means it is a sawtooth kind of road condition is there. When we are means coming down, what is the thing? Means like can I stop the engine and come down slowly to the end point? Okay. For crawling up, we need more power. I will reach the destination. While coming down, I will switch off the engine and can come down. Huh? Is it the good way? Yeah. What happened if I stop the engine and I will come to the down? I can't. Means like if I stop the engine and I will come down because of movement of inertia, it will come on its own. But what happens? No, means like I can apply the brake, mechanical brake I apply. What happens? Can I come? Is it the usual practice in our country? Means like from upside I will apply more force, I will reach the destination while coming down. No, no, don't talk about the hydraulics. You come to our electric part itself. Now, what happens? Now we are making use of either DC motors, DC machines, or induction machines are there for our system. What happens? Hmm.
Like motor or this thing.
Hmm.
When you are going to turn off the ignition,
Hmm.
the steering control will also is unable to control.
Okay. Yeah, one is the rightly pointed. What we can say that the control, we will not get the full control over the vehicle. With the engine only, that you know that you are much familiar about the torque speed characteristic. So with that you will have the good control over the system. Otherwise, it moves on its own way, we will not have the good control over the system. We have to come with the starting the engine only. Then only that means like we can get the control over the speed of the motor, machine part. That is the thing. Okay. For that, during that process, it may not require the more. It may not require the more amount of current, but only that the voltage maintenance is required. This one. So here that the storage, wide variety of storage technologies, means like DC-DC converter, dynamic braking, and also energy and power management. These are the things that it is essential to realize your system. Okay, we have to have. And storage technology, that selection of wide variety of energy storage systems technologies are available. Selection of energy storage systems for a particular application depends on the power and energy rating required for the required application, response time, weight, volumetric conditions. You know that you want to talk about more about the modularity of your system. My system here that you are into that professor is speaking about the high frequency and the low frequency. That what's the basic difference that you can get from high frequency, that the mobile phone that you are having the charger, and the conventional line frequency transformer that you are having. What's the difference that you will have? Yeah, compactness, that the size. Means like if you make use of the line frequency transformer, it is of so big, and then high frequency transformer, it is of very small in what we can say the size. It is compatible. Okay. Here also the same thing, that we will see that the response time, weight, and the value. So we are modularity, that you want to see that if it is of, if there is of any fault in module, we can so easily replace that faulty module and the system can be run. That is one. And these are some of the storage, global cumulative energy storage installations across the globe. We got it from one resource, that is the Bloomberg NEF, and that we projected. These are the things. Now, if you see that the review of storage, energy storage technology, that we will talk, we will store the energy for sustenance, longevity purpose, and I think you have mechanical type of storing the energy, electrical storage, and the chemical energy storage. Okay, and these are of mechanical. You know that this I will talk about this flywheel energy storage system. Okay, and it is well proven and mechanically. What the problem with the flywheel energy storage system? Can we make use the flywheel for our electric vehicles or of distributed energy sources? That the flywheel energy storage system, can we make use to electric vehicles? Okay. Weight is a constraint, and also What? Okay. Okay. And that one thing I think professor is also here. They are working on this flywheel also. The thing is that associated with the speed. Speed is going to very high in the case of flywheel energy storage system. It can be of we'll talk in means like in terms of the 20,000, 30,000 rotations per minute. That the bearing has to support that kind of speed. If the speed is more than this one, then the flywheel flies away from the system. So then that is the problem. Means like that the power electronic equipment also associated this one. Then it says that electrolytic capacity means like electrical energy storage, that it is going to make use of the supercapacitor. One thing, what it is going to do, electrofield, it stores the energy in the form of electric field, and then magnetic field. This one stores the energy SMEA, but it is not at that I am saying. It is for only for reactive power compensation, short to purpose, that short duration, that we are going to make use of this SME devices. Even this supercapacitors also, that we can't say that it is provide the means entirely for the longevity duration. Short duration purpose, that the supercapacitor that can be made use, and it is works well with the combination with the other storage device, not alone sustain for long duration. This one. And then chemical, that you are more familiar, that you are having the resources, that the material is available. So then the world is looking on this battery storage system. But lot of research supposed to happen. That you people are talking about this Chinese people and the USA, South Korea and Europe. They are working on this one battery to increase the capacity of the battery. So that the capacity of the battery, how you are going to analyze the capacity of the battery? Capacity of the battery. If you want to select one battery, what parameters will you look into that? Ampere, and then voltage rating. Yes, that the 12 volts batteries, 24 volts batteries, and the 48 volts batteries. And our DC bus system also is that kind of nature. Yeah, fine. 12 volts, 24 volts, and the 48 volts, that will be. And is it made that the one single cell can make the 12 volts? Yeah, one single cell can make the 12 volts. Battery pack, that we'll call it as a, if you want to have the 12 volts battery system, it is a kind of a pack of cells which are connected in series to increase the voltage rating. Yes, that is, you know that individual battery can't give the 12 volts, that you require the small cells which are connected in series fashion to get the 12 volts rating. So then fine, if one man is there, it is very easy to get control. But these are so that the population means like many people are there, how we can get control over them? Yeah, one I want to move fast, and other one wants to be sleepy, he don't want to come forward, and another one is doing the average performance. How we can balance? That the cells are there, but system is one. System is one. That is the problem, that what I am trying to say. Are you getting? Means like that 12 volts is required for us, and there are many cells which are contributing to get the 12 volt. One is performing well, which is near to me, and the other one is not performing, means like in the middle, and the other one is drowsy. He don't want to react. Yeah, series. Yeah, that series combination will give the higher voltage rating, and the parallel combination current rating, that it is well established. Then okay, that series parallel combination is there, but individually I am talking this person, that person, they are not performing well. How should I do? Yes, that is some kind of balancing technologies that we require to. We have to monitor the individual cell voltages, and then if it is not performing well, then we have to what's the problem with that. Then we have to identify the problem and get it solve their problem. Okay, balanced way usage of the batteries will one technique that we can say that if we can enhance the lifespan of the battery. That technology what we are going to call it as a cell balancing technology. Okay, this is the cell average performance of the cell that can be taken into the account. Then we'll work on it. That is what cell balancing technology that we'll see that. This is one thing. And then magnetic, no, okay, I can give. And the fuel cell also, that may not be, I can say here that the chemical energy is converted to the electrical energy. What will happen in the battery or of fuel cell, that the one compartment to the other compartment, that the ions are going to move. It is depending on your chemical reaction that the ions are going to move this side during charging part or of discharging part. And in between that the battery performance will go down because of the chemical degradation, that the quality of the material is going to decompose and then it won't give the proper performance. That one thing. And also there are some high capacity batteries are there that I am making use of the single word. I don't want to get in depth about the batteries part. Batteries that I am saying, nickel, cadmium, lithium ion, lead acid batteries, hydrogen batteries, these are of a wide variety of the batteries. As an electrical engineer, I don't want to disturb the chemical, I don't want to disturb the physicist, I don't want to disturb to the metallurgy people. They are working, it is your zone, okay, let it be your zone. But when it comes to as an electrical engineer, I don't want. My portion is of battery, how to manage the battery. Means like with the increased lifespan, means like that the usage of the power converter. Power converter are going to be helpful for charging and discharging. Okay, that the power converters what we are going to do, charging and the discharging of the battery. That you can do simply by connecting, but internally what it is happening that you are supposed to know. That it requires to have a kind of our household appliances is made up of AC power supply. Battery is of DC. In between there should be of a conversion. That conversion, what type of conversion it is going to be? Rectifier one phase. Okay, that you will get from the rectification. You will get the pure DC. If you make use of 3-phase rectifier or of 6-pulse rectifier, 12 pulse rectifier or of 20 pulse rectifier, can you get the pure DC? But you will get it pulsating DC, you are going to get it. Then you have to stabilize by making use of what? Filter or DC link capacitor that you will call it. Okay, that the DC one capacitor that can be placed and it eliminates all the harmonic, then the pure DC you will get it. Okay, that if you take the rating of your household, it is of 230 volts or of 220 volts, that the single phase system. Then the DC obtained is not the, means like around what you can say that the rectified DC. Means like if 220 volts, that the input source, what's the output? Depends on the secondary. No, here you are having the rectifier. Yeah, Vm by 5, that the expression if you apply, you will get the DC. But my battery is not rated for this voltage rating. Yes, that is the second stage is going to be that what we can say that it is a kind of a DC-DC converter. That the output of your rectifier will be given as an input to the a kind of a step-down converter or of a step-up converter. Okay, to match the voltage of that one to your battery. Okay, this is the stage will be there. So then DC-DC converter. You know that it will be DC-DC converter, you are familiar, and that most of you yesterday's, I think yesterday or day before yesterday's class, their campus wants to have the DC power, DC bus for all the, their campus wants to have the DC power supply. So DC power supply for all their data centers, all their equipment, they want to have the DC power supply. So DC is much preferable as compared to the AC power supply. It is a debate also that I can say that DC is more highly preferable as compared to the AC power supply. So then what's the advantage? That you know that it is portable, more portable than the DC, and we can have the means more portable, that is one thing, it is independent. And then also now because of the advent of this power electronic devices, that we can step up or step down the DC voltages, like step down converter, we'll call it. Yes, no frequency component is involved, and also that we may buck operation or a boost operation, it can be. Here also the same thing in the case of this batteries part or of supercapacitor part, what we are going to do while charging and discharging. Charging means like what we are going to do for a battery or of a supercapacitor. Now you say that, now you say that if the battery is fully charged, what does it mean? Or of a one storage element is of full current. Okay. Now I will say that my mobile phone is fully charged. What does it mean?
All the dipoles in the battery is engaged.
Okay. All the?
Dipoles.
Okay. Oh, no. I don't want to be that much complication about dipoles or movement of the thing. But simple our electrical. Electric terminology. Saturated. Okay. Saturation means? That the voltage rating of your battery is close to the, means like that the charging voltage of your battery is close to the rated voltage. Then you will say that the battery is a fully charged condition. Okay. Then the voltage rating of your battery is going to be like a rated voltage. Then that is the battery is a fully charged condition. Then it will be, means to give the good performance. Okay. That is what. That the charging means here, charging operation, how we can relevant this one with the power electronic system. Voltage rating that we have rise to this battery level. Yes?
Depending upon the SOC, state of charge, we are going to plan.
Okay.
Whether we need to charge with the constant voltage or we need to charge with the constant current.
Okay.
It is more than 80%.
No, you charged the battery. Now the charged the battery. What operation means like you increased the voltage or decreased the voltage. Suppose that you increased the voltage. What kind of operation it is going to be?
Boost operation.
Increased the voltage means like it is of a boost operation, you will say that. If you decrease the voltage, buck operation. These two modes of operation that can be performed with the storage technology. Okay, either it can be of a boost operation or kind of a buck operation. That you are having this single leg inverter structure, off leg inverter structure. It acts like a buck conversion or of a boost conversion. That can be exploited, means like for charging and the discharge. So these things that we are having, electrical energy, chemical energy and the mechanical energy storage technologies are available. And each one is having advantages and its disadvantages. This is what we can say that. Now if you see that the energy storage technologies and in terms of the efficiency, energy density, power density, life cycle and the response time. Response time also it matters, means like I am not a respondent for your requirement. Then what is the use of my presence? So that the response time also very important. Some of the things that among this kind of response time, that the supercapacitor response time is much faster as compared to the other types of storage systems. Okay, lead acid batteries, flywheel, compressed air energy storage system, pumped hydro energy storage system. This chart also, what we are trying to project here, that the power density versus energy density, okay, watt-hour per kilogram, means like you see that ultra capacitor, and also we will call it as, there are 3 or 4 different names of this ultra capacitor, pseudo capacitor, super capacitor, that double layer super capacitor, that we will call it, this one. So then SMES over and above, it is having high power density then as compared with the batteries or fuel cells, okay. Even aluminum electrolytes, that it is having the more, what we can say, that the power density. And it can be made use for the short term purpose, not for the long term purpose. This is the means the comparison table which we provided to make you to understand the different types of storage technology. These are, other than this one, you have any other storage system? Other than this type things, that you have any other storage system? Yeah, fine. Okay. Now we will make it more mature about this technology, because you know that India is the largest exporter of the batteries to the rest of the countries. Okay, even either for 2-wheelers or 4-wheelers, and our people are smart enough to manufacture the batteries, and then they will export to the, even for other developed means other countries. Then this one, that the chart, these are the components that we are going to take into the consideration when you go for the selection of your storage system. Efficiency part, energy density, power density, life cycle, and the response time. That the lifespan also very high in the case of a supercapacitor, okay, more than 100 million hours that you will experience, okay. And then this flywheel also, its lifetime is okay, reasonably okay, only it is associated with the mechanical part, that if you can maintain the bearing and that thing, that it will be well and good about this one. This one are of hydraulic, that arrangement, pumped energy storage system, 20 to 60 years. And then this lead acid battery, you are more familiar, but the lifespan is very less, okay. 200 to 2000 cycles in their life, okay. So this graph helps to help us to determine the energy storage combination to build the hybrid energy storage system, okay. Why we want to go for the hybrid energy storage system? The efficiency of the lithium ion battery is higher as compared to the other. The efficiency of the lithium ion batteries is higher as compared with the other storage system. It is not so, okay. The supercapacitor is having highest life cycle, that is greater than 1 lakh, means 100 million cycles, okay. And then it is having the highest power density because of the absence. Again, I am stressing the point, because of the absence of the dielectric material in the case of supercapacitor, makes the energy, means the area to be bigger, that the capacitance is proportional to the, what we can say, area of the system. Area is bigger, that the capacitance is very big in this case. Then this one, efficiency, okay, depends on the choice of storage system, depends on the system requirement. Generally, high energy density, high power density requirement may not fulfill by using the single energy storage device. The motivation to go for the hybridization of your storage systems, okay. One single storage element can't satisfy my requirement, okay, in terms of the response time, life cycle, and efficiency point of view, that's the thing. So then, that the maturity of your things, what we can say, that the supercapacitors are not into the electric, he is saying, means like some Europe, they are saying that it is developed in there, but in our country it is not so, okay. They are not clubbing with the batteries with the supercapacitor. That still some means like standardization is going to be required to use the supercapacitors in electric vehicles. Have you come across anything like that our storage system combined with the supercapacitors? No, not yet. I mean to say that I myself also not yet see. But air, air, no, no, air is not the dielectric. Okay. Here, what we can say that the dielectric material, that epsilon naught is there, na? That the equivalent air is also that the permittivity that will be taken into the consideration. Uh, uh, mm. No, that is a kind of chemical that will be poured in it, and that the more space is available, that the chemical content means silicon carbide kind of material will be there in it, that will be transferred the means like ions will move from one plate to the other plate, that the accumulation is going to, ions diffusion of the ions from one plate to the other plate is going to happen. Not in dielectric in nature. Okay. High power means like that's what we are saying na? In electric vehicle, that is the starting conditions, you require the more transients that you do experience in the starting condition. Suppose you are starting your engine from 0 kilometers per hour to the 100 means like 100 kilometers per hour. During that condition, you require the more amount of current that can be taken care by the supercapacitor. That graph also I will show you. Yeah. High power and the energy density, when you are having the 100 kilometers per hour, means like you will run it, that time that it requires the less power. So then, yes, this is the thing, that the concept of why we want to go for the hybrid energy storage system, this is the motivation. Now, if you see this one, okay, this is the sample thing that I want to project, that the flywheel energy storage system, that the main for the higher speeds, that is 20,000 to 30,000 rotations per minute. Okay. Then system. Okay. This is the what I mean to say that the internal resistance, equivalent resistance is going to be 0. Then it can conduct the more. But it is inductive coil, but we have to maintain the superconducting states. Okay, by using liquid helium, liquid nitrogen, we have to maintain the superconducting state. Then only that the storing is going to be possible, and it is meant for the short time power short time power compensation, means like in order to some disturbances is there for 15 seconds to less than 30 seconds, that we can make use of this superconducting magnetic energy storage system. And it also requires, you see that this kind of multi-level inverter, and it is a 250 kilowatt system, 1800 volts, that it requires major component, that the equation stored in the, means like high inductance. Okay, high inductive coil is required. How many of you seen, means like the maximum inductance in your life? Maximum inductance. That inductance, millihenry, or of at the maximum, that the millihenry is condition that you might have seen. But even if you see that a kind of 1 Henry, that the size is going to be this much bigger, 1 Henry. 7.5, yeah, maximum of 7.5 millihenry, or of means like in terms of the millihenry that you can see. But if you go for 1 Henry or of means like 10 Henry, that the size is going to be very big. Okay, and we are supposed to maintain the superconducting states, means like that the cooling system, cryogenically cooling system, and this power conditioning circuit, superconductor coil is required. This is the stored energy equation, means like it is not a rocket, means a big complex equation in the case of superconducting magnetic energy, that the energy stored across an inductive component, stored across an inductive component is taken into the consideration. Okay, these are the things, and some applications: energy reserve, voltage support, reactive power compensation, and then harmonic filtering part. So now it is more somewhat interesting to know more about this thing, and long time that we are seeing this battery pack. Here also that I will give the specifications of this one. This is of 58 farads and 15 volts. Okay, two supercapacitor bank modules are connected in series to get the 30 volts operation. Okay, that the voltage rating in the case of supercapacitor is of very less. Even small, for getting this 15 volts also, that we externally 2 modules are connected, but internally if you see that 6 cells which are connected in series, here 2 cells, here 2 cells, and here 2 cells. Okay, that makes you to get the 15 volts, that you can divide by 6, you will get around what we can say that 2.95 or something, 2.5, 2.75, that you will get it. Now the problem means like if one person is there, that will be well and good, but more number of individual cells are there, we have to monitor each and every cell voltage, then make you to be balanced, make it to be working conditions. Okay, is it fine? Okay, now my way, or can I come to you, make you to be alert? Then is it okay? Once again, fine? Or any queries so far? Or anything that you want to pose? That thing? Hmm. Hmm. No, actually we have the theoretical knowledge about this flywheel energy storage system, for me, from our references, this is the content what we have received. Means in the sense that we are not actually working on flywheel energy storage system, but it requires for charging and discharging also it is going to make use of this power electronics equipment. Any? That in olden days, means like if you take the hydropower plant, that all the hydropower plants are fitted with the flywheel only, not with like conventional battery or of supercapacitor part. Still it do exist, but in practically near to the hydropower plant that we can see that the flywheel energy kind of storage. Any answer for this one? Okay, yeah, that is the means for hydropower plant that they are going to make use as per the.
We are going to store the energy in the flywheel.
Hmm.
Suppose we are going to move the wheel, some 25% of the part we are going to supply some mechanical energy. Then by the weight of the wheel, we are going to get a high speed.
Yeah, means like if you are storing the energy, it moves to the upward level, and then that it is supposed to maintain, then it is stored the energy. And if you want to discharge the energy, that the flywheels will come down and then discharges. Okay, that is the operation. After reaching to the flywheel at higher level, it has to maintain that level.
I think we are going to use while it is discharging,
Hmm.
the motor what we have there, that is working as a generator feedback to the system.
Yes, yes, yes. In that way, a bi-directional way that we are going to make use. Yes, that is, while charging, it moves to the up and maintains that level, and while discharging, that it is a kind of circular disc. I mean to say that the circular disc, it moves to the up and maintains that height, and while means discharging, it comes down, and the height it is going to be decreased.
Is operating as both motor as well as generator.
As well as generator, yes, that is. Okay, this is the theoretical knowledge that we can say that. And then major focus is on our hybrid, means batteries and the supercapacitor part. Yes, fine, we will make a move. Yes, this is the supercapacitor. Now we can say that here that the 6 cells which are connected in series, and that the external connections are provided, and 2 modules which are connected to get the what we can say that is the 30 volts operation, we can say that. Here these are known as ultra capacitors, electrochemical double layer capacitor. Supercapacitor store the energy by accumulating, means it is going to store the energy by accumulating positive and negative charges and store it on 2 parallel plates separated by an insulator. Okay, 2 parallel plates, not the dielectric medium, it is a kind of insulation will be there. It can be charged and discharged faster than batteries. High power densities, means like this is what watt hour per kg, it is L supposed to be kg, but low energy densities 10 to 20 watt hours per kg. Then supercapacitor is well suited for applications of high power within short period of time, that well known. And then supercapacitors can be arranged in modular system by paralleling and serializing in order to increase the power and the storage capacity. That we are saying that conventional electrolytic capacitor, that you are having the voltage rating is higher, whereas when it comes to here, that the supercapacitor part, that the voltage rating is lower, that you require to have the what, that the series parallel operation is required. That can be done, but it impose some other problem. What the problem? It is going to impose other problem, voltage balancing. That the voltage balancing unbalance is going to experience, that can be made. And then one more beauty of this thing, that we mentioned about the 58 farad and the 15 volts. What about the current rating? That the working current rating of the supercapacitor. Yes? Any one of you that you say that your conventional electrolytic capacitor, what's the current rating of the, means that the working current rating of the capacitor? current rating that can be operating rating electrolytic capacitor. Milliamperes are of ampere at the maximum amperes that you will get it. Yes, and the voltage is of line voltages that it can be 1200 volts that. But here this current rating is going to be very very high. This one is made use up to 1200 amperes. 12 I think I have I think yes. We have yes 1500 amperes, that the maximum peak current for the supercapacitor is of 1500 amperes. That you can imagine that in your laboratories, okay, that the current rating is of, it will not go more than 10 amperes or something. But this with this model that we can work with the 1500 amperes. Yes, this much size. And what we require, current conditioning circuit is required. We don't have the power supplies which are rated for the 1500 amperes. So then we'll scale down, and the current conditioning circuit is going to be employed if you want to make use of this circuit. Okay, that the current conditioning circuit. Then this yes sir. But bulk modules are required, sir. Means like we can getting the voltage rating, that is, and also it can't be used. Specifically, we have not seen completely taken care by the supercapacitor, but it is not possible, and it. No, that it is one thing. There are two things that we can say that if you wants to completely make use of the supercapacitor part, that the size is going to be very big. That is first part, and the second part is of the cost of your supercapacitor. Means that the cost is of exorbitant. That it is means like not like ordinary electrolytic capacitors. So that the cost point of view as well as the size point of view, it is going to be a bigger. As on date, that it is meant for the short time, that we said means like not more than 1 minute time period. Okay, that your transient period, how much time does it exist? Transient period. Yeah, maximum of 30 seconds or of 40 seconds, means like maximum 30 seconds do exist. Then once if it is started, then it moves to the rated speed. That purpose it can be made use. Yeah. So then if you come to this portion, that the lithium means like again I have drawn the means that the work with this one 58 farads also for me too much big. What I did, that the series connection, that the 29 farad voltage we increase, minimum voltage this one, maximum, and the equivalent series resistance is of this much. Okay, that we have done. And then available, these are of 6 watt-hour, 58 farad, 30 watt-hour, 5000 farads are also available in the market. Okay. Now when it comes to the battery part, okay, that it is what type of form that it is going to be stored? Chemical energy. It is in the form of the chemical energy, I mean to say that. Yes, chemical energy, that we have this kind of battery. Battery is having, yes Swami, is having any, yes, you have any discussion? You, anything? Any points to add?
These are basically we are going to use moreover lead-acid batteries because of cost constant.
Okay.
Whatever home UPS, whatever it will be, we will go with the lead-acid batteries.
Okay.
Nowadays the batteries using for the vehicles, for starting purpose, all those lithium-ion battery, that is for the purpose of the maintenance.
Okay. Yeah, fine. Means like that we are saying again the means that the statement it is fine. We don't want to disturb the manufacturers about the batteries part. As the electrical engineers, we are the end user. They will give, this is the specification, these are the life cycle, this is the rating of your battery. Then we have to use the battery. Now, this is the performance that we are going to look in terms of the energy efficiency, energy density, power density, life cycle, and the self-discharge. If you won't make use of the battery also, then what happens? That it self-discharges because of the presence of the internal resistance which is present. That itself. Even the electrolytic capacitor also, if you won't make use that electrolytic capacitor for some time, okay, then it discharges, self-discharges. Because of what? Because of electrolytic capacitor, you means like if you see the TV, television, that you start and LED, immediately you take off the power supply. LED instantaneously won't come to the off condition. Slowly it takes and becomes completely off. What is the reason? You know, one television that you can turn on the television, then you can watch the movie or a favorite thing of your interest, then you will turn off. Immediately as soon as you turn off instruction to your television, it won't come to the off state, that the LED. LED will take 5 to 10 seconds to completely discharge and become off condition.
Because of the energy stored in the capacitor.
Yes, that energy stored across where?
Across the LED.
Yeah, that LED is there. LED that you are going to make use of a one capacitor is there. That the capacitor is going to have the two types of resistances. One is series resistance and the another one is a parallel resistance. One resistance is responsible for the charging condition and the other resistance is responsible for the discharging condition. Parallel resistance. That is the, you know that the time constant, RC time constant is there, it is responsible. It is not linear, it is like a exponential charge and exponential decay of the capacitance. Okay, this is what it is going to happen. So here, that the lead acid, nickel cadmium, nickel metal hydride, lithium ion, lithium polymer, sodium sulfur, vanadium redox batteries, these are things are there. Some specification that we are going to see. Various types of battery technologies and its properties that we are going to see that. This is some data that you will means like we obtain and for selecting the optimal battery for our application, that we can see. So now this is one thing that what we can say that this is the challenges posed by the batteries. Okay, if you make use the batteries part, okay, this batteries, what the challenges? Now I said, means like that maintaining one is a good performer, one is a bad performer, and the average performer. How you want to maintain all the members in my group? Okay, similar to like our classroom. A good one excellent student, a bad student, and the poor student. Who are going to be my student? Yes, all are my students. My question is that even my professor used to quote this thing. Okay, all are my students only. But you know, as the excellent student, if I tell the concept, he won't follow. Then why means like he knows more than what I am. Then he will say, sir, what sir is saying, it is not applicable for me. He will neglect me. Okay, and poor student, how best that I am trying to convince him, but he won't be convinced. Then what's the point of going for the poor student? Then the average students are going to be my students. It means this is they can be flexible to jump to the higher level, or they are flexible to come. But usually, as we are there, they will make them to the next level. Okay, and that is one. Here also the same thing, that we will monitor the individual cell voltages across the, means like how we are going to monitor that the cell voltages by making use of the some kind of sensor, either voltage sensor, current sensor, temperature sensor. These things will be there that will monitor. If it is not performing well, that will have some kind of charge discharge mechanism will be there by using the inductance or of capacitance. Then they will brought to the same condition. You see that cell balancing is not taken care by all the electric vehicles and also helps in using the full potential of the battery. Okay, if it is not used in a balanced way, we will not fully utilize the battery capacity. That we have to have the concept of equalizing the voltages. Once again, that the cell balancing is not taken care by all the electric vehicles. It helps in using the full potential of the battery. Okay, if you are having the balancing maximum voltage, that point also did not come to me. 12 volts that you said, 24 volts that you said, and the 48 volts that you said. Yeah, fine. Even 12 volts we can't manufacture. Okay, then what maximum, that the 2 volts batteries are of very standard in high power application. In railway engineering or of substation, that the 12 volt batteries, but the ampere hours are going to be more, not more than 12 volts. 12 volts, if they want to have the 110 volts DC supply, they will connect the 55 cells in series. Okay, that the 55 cells are going to be in series to get the 110 volts per DC relays will be there for operation purpose. So that the cell balancing technique is of very, very essential. Why? Means to avoid the chemical degradation or maintaining the safe operating of the battery, that the cell balancing technique is required. Inconsistency, obviously something we don't know, we can't estimate. It is a complex chemistry of the battery. Okay, how best I design the battery model, I can't predict the behavior. Okay, that even big companies, big personalities are cracking their mind how to predict the behavior of the battery. That the battery, we can't predict the behavior, that how it is going to be react also, that can't be not so easy aspect. And best models also which are there, that even in your MATLAB also, that you can find the battery model, but you can't get the required parameters. Okay, only that the current voltage rating, current, and the age, that the capacity will be there. But the internal resistance, that I will show the battery model also, that is thing, but you can't get all the parameters what you require to develop the complete model of a battery. Then this one, inconsistency is inevitable for series connected batteries due to manufacturing and usage factors. Okay, different applications. A battery balancing system is effective method to ensure that the battery performance and lifespan are maximized, preventing the battery from overheating, overcharging, and over discharging. These are the things: overheating, overcharging, and over discharging. This slide, I can say that it is one of my undergraduate students done the simulation work. I am making use of his results. Okay, and good. The person has taken the novel concept to work on this cell balancing technology. Okay, this is what here, that nearly 5 cells are there. He has taken the example, and individual cells here in A part, that okay, 2 cells are performing at the optimum and the other 2 cells are at lower level, and then this one here something. But here what we are doing in the C and D, that we have, after applying the cell balancing technology, that some of the charge which are excessive in other cells, that can be transferred to the cells which are having the lower capacity. Similarly here also, that the thing that we can see here also, C and D images. So now this is something about the battery part. Batteries, what we are saying, that it is associated with this kind of disadvantages. Only for, it is meant for the energy density. then we have to go for the hybridization for longevity purpose, for enhancing the battery lifespan. You take one example, what we can say that LEDs are there. Most of you are aware about the light emitting diodes. This light emitting diode, that the lifespan of the LEDs is more. Lifespan of the LEDs are more. But if you are going to make use of the electrolytic capacitors, that is more than 20 years, that the LED's lifespan is going to be very, very huge. Okay, that the lifespan of your electrolytic capacitors. What the lifespan of your electrolytic capacitor? Not more than, means like 2 years. Means like that the number of cycle, that we can say that it is not more than 2 years. Then we have to have LEDs are of stronger and the storage elements are not that much stronger. So that the combination, that there are some topologies associated with the supercapacitors part. Yes, then this one here, most of the applications demand a combination of energy, power densities, cost, life cycle specification, which can't be made by any single energy storage system. Okay, that we require to have the dual storage system. Hybrid energy storage system, electronically combined, that the power densities out of 2 or more energy storage systems with complementary characteristics. Complementary means like one opposite characteristic, that will combine, will exploit the features of those combination. Okay, that the combination of anything, a few examples that I quoted here: supercapacitor, pumped hydro energy storage, SMA, compressed air, flywheel, fuel cell, battery. But here I means like did not mention about the supercapacitor versus battery also. Okay, hence hybrid energy storage system basically consists of high power devices which are of responsive, very fast responsive, and high energy devices, slow response, for example the batteries part. Okay, now so far anything, now we will enter into the other part. Yes, any query that you want to make, or any combination that you want to make, comment? Any? Which one?
Actually, battery actually is 2 cases.
Huh.
High power as well as high energy. The battery has the ability to supply those two.
Which one? Battery means transient, I mean steady.
Different cases is there. High power density as well as high energy.
Yeah. It is there. Means like, if I am new, I can, if I am young, I can act. Okay? If I am old, I can't act. Then who are going to be the loser? That the load is going to be the loser. Means like what we are saying, that load is always master, that the follower is of a source. Suppose that the operation means like I don't want means like this is critical loads, that if you are going to take an example, they are in stringent requirement. Okay, if frequently our mics also, that we are putting the new battery into it, I can survive with the old battery also, but in between if the interruption is going to happen, then we are the sufferers for that. Quality is going to be degraded and the lifespan is going to degrade. That is the intention. We don't want to make use of the batteries means like for transient condition. But electric vehicles also, even till today, they are making use of the same thing, but the performance is less than 1 year, or of every, I think 2 years, 3 years, that you require to replace the.
Some vehicles is there, sir.
Okay.
Around 1.5 years we need to change the battery.
Yes, that it is expensive solution as well. Can you offer? I am not that much rich enough to offer the thing. Till even my two-wheeler, that I am sustaining okay with the IC based engine. Okay, and then it is the technology is improvising. Now people are talking about this global warming and ozone degradation and green effect gases, all the things. So now the technology is improvising and we will get this thing. Okay. Yes, this is the combination. Any other things from your side? Fine. Now your Can we move to the next? Okay. Now the power electronics part will come, where how the power electronics is going to play role for this kind of storage system. We have the two different that madam is conveying, that the passive parallel structure, cascaded structure, active parallel structures are there. And you have to have the operation. What we can say that it is storage system 1, 2 and the associated power electronics converter, and the output of this one will be given to your system, or it can be of a load. Or two storage systems are there, separate controllers can be given, and then cascading of this one that will be given to your load network. Okay. Here only one controller is required, but here two controllers are required. Okay. In the case of active parallel structure, that you require the three controllers. Okay. Three controllers are required. So then which one is good? Which one is means like preferable? Yes. Hmm? Uh-huh. Huh. B. Okay. But my choice is of third one, active, because we want to monitor the individual cell performance. So then it is better to know that what it is happening, that the individual storage system, then separate converter should be there, then it will enhance the performance. Individual cell, individual controller is required, and the combiner. If one controller is under failure, then that will be taken care by this third controller also. Okay. But even though it is of some more components augmented to the system, but it is of more effective as compared to these two. Okay. That we'll see that what it is expected thing in this controller, what it is going to be, that the controller power electronics device or a power electronic controller, what it is going to be. Yes, that is the bidirectional DC-DC converter, that the power flow that can be made from the source to the load or from the load to the source. This is one. And then this converter is there. Then we have to operate this converter in what mode of operation? Either closed loop operation or of open loop operation. Closed loop operation. If you go for the closed loop of operation, what type of parameters or controllers are required? PI controller is required. Okay, that is a type of a controller, but you know how what for PI controller, what parameter that you want to control? Voltage alone? Yes. So then each converter module contains the two loops. Okay. One is the external controller, another one is of a inner controller. That we will say that voltage controller, and the other one is of a current controller. That the transient that can't be passed from the source to the load side. Okay, that the current controller is there, so that your system is going to be safeguarded. That is what we can see there. Yes, that is always that the current inner, that's what we are saying, that the disturbances can't be transferred from the source to the load level. It can be mitigated at the source level itself. With that we will measure the external voltage, inner current. That we will not take the output current. It is the input current that we are going to take into the consideration. Outside, yes, that is the output voltage. Okay, that the current is across the inductive component. Inductive component can't be the output current. Okay, you have the one more stage. Yes, this is. That's what we are saying, means like individual to control both these controllers, that we have the third controller. Okay, and it can control individually that the storage system 1 and storage system 2, but to control over means like I mean to say that the third controller you are getting two inputs. I want to share the load equally. Then I may fix. I want to make the control like this, 25% by one thing and 75% by one thing. That can be controlled by externally. Okay, by setting this one, that we can have the contribution of the individual converter. 25, 75 or 75, 25, 50, 50, like that, 10%, 90%, that depending on your profile. Okay, that the what we can say that the performance profile accordingly, that the sharing of the load is going to take place. Yeah. Next. Yes, fine. We'll make a move to the next. Yes. Okay. These are the structures that I mean to say that now with the converters, without converters, number of converters for the different system. That this one is nicely projected by my student only. Passive hybrid energy storage system configuration A and B, and the semi-active hybrid energy storage system configuration C and D, active hybrid energy storage system by E and F. That you know, here in this case that the number of converter, DC link voltage, controlled battery current, controlled supercapacitor, DC link voltage configuration. These are the things that we are going to have. Means like all the time that you know that the flow of the current either from the source to the load or load to the source side. Okay, this one here if you can carefully identify this structure, there won't be any energy exchange among these two. Okay, but we are transferring to the load or load to the source part. Here we can see that, but there won't be, that is the new topic, means like already there, but we are working on the energy exchange among these two sources also. Okay, and here I think he has taken only two sources are here. We may augment one more source as well, means like that one we can keep the PV panel, that is also there. I will show the structure. So these are the configuration, that the number of converter for the configuration A. Here it is not making you any converter. B converter, it is only one converter. Okay, see that if you see that one converter, D one converter, and then this E two converter, and then this one is a one converter. And then controlled DC link voltage, no, here it is not possible. B, yes, okay, yes, yes, yes in all the cases. Controlled battery current, no, no, and here yes, no in the case of D, yes, yes, okay. So controlled supercapacitor current, no, no in three cases, and yes, yes, because separate controller that we are making use. And then DC link voltage swing, less in the case of first four cases, and it is high in the case of last two cases. This is we can say that the relative comparison of the passive, semi-active and active hybrid energy storage configuration. Okay, each and we are going to have the elaborative discussion on the individual converter, that is the bidirectional DC-DC converter, and that some test performance by injecting some disturbances at the source side and the load side, that we can see. Now the thing, any other things that you want to pose at this stage, any questions? Fine. Now I will show you the simple controller for this one. There are three layers of the control structure that you can find. One is the outer layer, and the second one is of middle layer, and the third one is of inner layer. That you can see that this is the DC bus we are having. Okay, we have power splitting, means like how the power is going to split among the different storage system. Only two storage systems that we have taken. What is the percentage of sharing the load? Okay, either battery or a supercapacitor part. Current control, and here that is, here it is outer layer is of external, and the middle layer it is of a power, that will write the control algorithm to split the power level, and the inner layer is of a current. This loop is much faster as compared to the outer layer that you are already aware. Okay, and then this is the some block diagram representation, and we have only not complex that the 4 switches are there. That the conventional like means 4 switches that we are going to employ. That the 2 leg structure only. That it is very simple, not that much expensive to build the prototype also. If the switches are of less, that we will go easily for the experimentation. So, as a power electronic guy, what you require, that if you want to go for some kind of journal, means hardware results are of mandatory. Okay, it is easy to build our prototype also. So then, this thing, inner layer controls the hybrid energy storage system current, outer layer regulate the DC bus voltage. Here, that the DC bus voltage, can you expect what's the power level of our circuit? What's the standard that you said? 12 volts, 24 volts, 48 volts, 110 volts. Yes? With this, can you expect? Yeah, obviously means like that the standard, I think 40, not even 48, less than 250 watts. Okay, our circuit board is of less than 250 watts. Okay, that 3 ampere source we are having, and the 15 amperes DC power supply source is available. Then the maximum of 24 volts or of 48 volts if you take, it is not more power level. That is the beauty of our prototype. Then the middle layer spread the stored energy in the system. Traditional PI, initially we worked with this PI controller, but some advanced controller such as sliding mode controller, model predictive control also applied for that system. Okay. Then this is the somewhat system configuration. Power splitting strategy, I mean to say that you have the, during the transient condition itself, that you have to reach to the from 0 to the transient steady state condition. During this transient transition itself, if it reaches to the 50% of your period, then the power is going to be shared equally with the, means like some algorithm will make the battery and the supercapacitor can contribute 50-50% like that. Simulation, we will define the means profile, means like voltage and the current profile that we will take. With that only, in place of power splitting strategy, that only that the voltage and the current component only that we are going to take into the consideration. I mean to say that if it power splitting strategy, it is equal, suppose that you have the 10 amperes of load is there. Initial requirement is of 10 ampere source. Okay, that the 10 ampere source I can give it equally 5 amperes to one storage and the 5 amperes to the other storage, other source 1 and source 2, that will be. Or I can give 8 amperes to one source, 2 amperes to the other source. That in that way that we are going to split depending on the profile. Means like if it reaching to the, why we are doing this kind of strategy, to reduce the stress on the storage system. Yes, we have. That I will show you. Okay, that will show you the block, what block we have done for this one, defining this one power splitting strategy. I will show the block. Okay, that period I will show the block. So now this is the idea behind the power splitting strategy, that we want to share the load equally to reduce the stress on single storage system. Okay, then this is somewhat means like here we made use for the AC machine, but you know this is actual our work is on this one, battery and the supercapacitor part, and this is the traditional off-bridge inverter model, and then this one and the exchange to the load circuit. Okay, this forms the complete. I will give the modes of operation of this one. This is what we can see, that either three-phase induction machine or of a synchronous machine you can make use, and based on this one we got the good response by the proposal. And then next, yeah, this hybridization, the importance, active parallel structure is the most widely used one because of its obvious independent control capability. Each hybrid energy storage system has dedicated power conditioning circuit, that is the power electronic, which helps in achieving the variety of control and energy management technique. Only demerit, it is going to be the one high cost, that is what high cost due to employing two independent power electronic devices for each individual energy storage system. Many multiple input converters have been proposed to decrease the cost of such system. It requires sophisticated control algorithm. Yeah, this is cell voltage rating is very small. Series connection of the supercapacitor bank is essential for the higher voltage rating. So this is what that I can say. Then yeah, up to now, if you have any queries, please let me know, or we can. Any queries? So many people are not that much well familiarized with this kind of things, that slowly very few people are working on this arena. I mean to say that some IITs and the IIT Madras, IIT Hyderabad, and I think in IIT Mandi also some people are there. So then it is very I mean to say that demanding arena to work on this energy storage system. They will say that no electrical contribution, but this much the contribution is very exhaustive, vast energy storage system. So yes, in my next class that I will start with the same thing. This is the proposal. In my next session I will take the block diagram, some results part, and the power converters that we will discuss on this thing. Yeah, there are many constraints that the people are not here to listen. Not only in the sense, not, I mean to say that if you take the battery itself, battery is, they will say that it is a mature technology, but it is not so. If some collapse happens, then who is going to take care of the responsibility? It is like a huge disaster, that the battery explosion, battery accident, battery disposal also, it is some series of steps are there to dispose the battery. It is not so easy. And then estimation of the performance is also investing, that the experimentation takes long hours to work with the batteries. It is not that much easy. And also that the control algorithm that we are developing, our objective to have this kind of power electronic system to enhance the lifespan of the battery. If you enhance at least for some period, we will save the significant amount of money. Battery, all the distributed energy sources are fitted with the energy storage system. Without that, you can't sustain, you can't imagine also that do they exist, the distributed energy sources. That is the challenges are more, and also that challenges are more, and the people are working to get rid of those challenges. Yeah, fine. Anything you want to add?
Got the point. You're good teacher.
You want to add that yeah, professor is here, and he has also had worked extensively on this thing. He is having more thing that he will give more insight into this storage also, and also good the things. Yeah. Fine. We'll break. Yeah, we'll break and we'll continue tomorrow. Yes, sir.